Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, difficult ideas are allowed to take their time, and the universe can be explored without anyone expecting you to sit an exam at the end. Tonight, we are turning our attention toward a star with a name that sounds less like a celestial object and more like the password printed underneath a router: EBLM J0555-57AB. It is not an especially graceful name, but the object attached to it is remarkable. This star is so small that, when astronomers first noticed it passing in front of a large companion, it looked as though they might have found a planet. Only later did the measurements reveal something stranger. This tiny object was not merely reflecting light, or holding on to heat left over from its formation. Deep inside, under enormous pressure, it was doing the work that defines a true star. It was fusing hydrogen. Before we go any farther, where are you listening from tonight? Perhaps you are in a city where the windows are still bright, in a quiet room where everyone else has gone to sleep, or somewhere the sky is clear enough to show a few stars between the rooftops. And what time is it where you are? That question is especially useful on a night like this because the light from EBLM J0555-57Ab has taken roughly 600 years to reach us. Whatever time your clock shows, the light entering our telescopes began its journey long before modern astronomy, long before electric lights, and long before anyone had the inconvenient task of remembering a catalogue name such as EBLM J0555-57AB. If you find this kind of slow scientific wandering soothing, you can give the video a like and subscribe to Science for Sleep. It helps more quiet listeners find the channel, including those who enjoy learning about nuclear fusion at an hour when most sensible people are thinking about pillows. You can also leave a comment with your location and the time where you are. It is always interesting to see how many separate evenings, mornings, and late-night cups of tea can gather around the same distant object. For now, make yourself comfortable. Let your shoulders settle. There is no need to remember every number, and no reason to keep track of every technical term. We will meet this star gradually, starting with the simple fact that it challenges the picture many of us carry in our minds whenever we hear the word star. Most people imagine stars as enormous things. That is a reasonable habit. Our own sun is about 1.39 million kilometers across, and it contains almost all the mass in the solar system. More than 1 million Earths could fit inside it by volume, provided someone had the patience, equipment, and extremely questionable planning permission required to arrange them. Other stars make the sun look modest. Some are so large that, if placed at the centre of our solar system, their outer layers would extend beyond the orbit of Mars or even farther. Astronomy often trains us to think in terms of vast distances, huge masses, and numbers that appear to have brought several additional zeros simply to make the page look crowded. EBLM J0555-57AB takes that familiar expectation and quietly removes most of it. Its measured radius is about 84% of Jupiter's radius, placing it in the same general size range as Saturn. The comparison is so surprising that it takes a moment to settle. Saturn is a planet. It has rings, many moons, broad bands of cloud, and a density low enough that it is often said it would float in a sufficiently large ocean. EBLM J0555-57AB is a star. It contains far more mass than Saturn, produces energy through hydrogen fusion, and belongs on the stellar side of one of the most important boundaries in astrophysics. Yet in terms of width, these two objects are close enough to be compared without needing a new scale. That does not mean the little star resembles Saturn in every other way. Far from it. Size can be misleading in astronomy. Two objects may have similar radii while being completely different inside. A balloon and a cannonball can occupy a similar amount of space, but carrying them upstairs produces two very different opinions about gravity. EBLM J0555-57. AB contains around 85 times the mass of Jupiter, squeezed into a volume smaller than Jupiter's. Its surface gravity is estimated to be roughly 300 times the gravity we experience on Earth. Standing there is not an option for several reasons, including the lack of a solid surface and the immediate problem of being exposed to stellar conditions. But even as a thought experiment, it would be a very brief visit. The phrase, smallest star in the universe, also needs one gentle adjustment. Astronomers usually describe EBLM J0555-57Ab as the smallest known star, or the smallest star that has been carefully measured. The observable universe contains an extraordinary number of stars, and we have not taken a tape measure to all of them. Somewhere another star may be slightly smaller. It may be hidden beside a brighter companion, buried in a crowded part of the sky, or simply too dim for our current surveys to recognise clearly. Scientific records are best understood as reports on what has been measured so far, not as declarations that the cosmos has completed its paperwork. Even with that qualification, the record matters. EBLM J0555-57. AB sits close to the minimum size and mass that a normal hydrogen-burning star can have. Below that boundary, an object may become a brown dwarf instead. Brown dwarfs form in ways that resemble stars, but they do not have enough mass to sustain ordinary hydrogen fusion in their cores. They occupy an awkward region between the largest planets and the smallest stars, which has led to many careful definitions and probably more than one long meeting with a diagram on the wall. Our tiny star formed with just enough material to avoid that fate. Gravity pulled its gas inward. The pressure and temperature at the centre rose. Eventually, the core became capable of fusing hydrogen nuclei into helium, releasing energy and supporting the star against further collapse. This is the same basic process that powers the Sun, although the conditions, rate, structure, and total output are very different. The Sun performs fusion on an enormous scale and sends enough energy across space to warm Earth from about 150 million kilometers away. EBLM J0555-57 carries out the same fundamental task with a much smaller supply of matter and a far dimmer result. It is the stellar equivalent of a very small engine that has managed to start and continues running with no interest in impressing the neighbours. The closeness of this object to the hydrogen burning limit is what makes it more than a curious record holder. If it had formed with only a little less mass, the centre would not have maintained the pressure and temperature needed for stable hydrogen fusion. It could have ended up classified as a brown dwarf. With its actual mass, it crossed the line and became a main sequence star, though one at the faint, cool, low-mass end of that sequence. A small difference during formation produced a major difference in identity. This boundary is not as visually obvious as the edge of a coastline. There is no bright sign in space announcing that planets end here, brown dwarfs occupy the next lane, and stars should keep left. The categories come from physical behaviour, formation, mass, chemical reactions, and the way an object changes over time. Nature is under no obligation to make those categories easy for us. Astronomers must infer what an object is by studying how it moves, how much light it blocks, how strongly it pulls on nearby bodies, what kind of radiation it emits, and whether the measurements agree with models of stellar structure. That is one reason EBLM J0555-57 remained hidden despite being a star. Small, low-mass stars are faint. Beside a much brighter star, a companion like this can disappear in the glare. Imagine trying to identify a dark red ember placed beside a powerful studio lamp, except both are hundreds of light years away and cannot be separated by walking a few steps to the side. The larger star dominates the light reaching our instruments. The small companion contributes very little. Astronomers did not find it because it announced itself with a dramatic flare, or because a telescope produced a neat portrait. They noticed a repeated dip in the brightness of the larger star. Every 7.8 days, the small companion moves across the face of the primary star from our point of view. During that passage, it blocks a small amount of light. This is called an eclipse or transit, depending on the context and the objects involved. The dip looked much like the signal caused by a large planet. That was not an accident. The WASP survey that detected it was designed to search for exoplanets. Its cameras watched many stars and looked for regular reductions in brightness, the sort produced when an orbiting planet passes in front of its host. Here, the planet hunting method found a star masquerading as a planet. The eclipse revealed the companion's size relative to the larger star, but size alone could not settle its identity. Gas giants and tiny stars can have similar radii. Astronomers needed to know the companion's mass. They measured the motion of the larger star using the Crowley spectrograph. As the two objects orbit their shared centre of mass, the visible star moves slightly toward us and then away from us. That motion shifts the wavelengths of its light through the Doppler effect. The resulting stellar wobble showed that the hidden companion was far too massive to be an ordinary planet. This combination of measurements gave the object away. The light curve showed a body with a planet-like radius. The radial velocity data revealed a star-like mass. Put the two together, and the result was an extremely dense, very low-mass star near the lower limit for hydrogen fusion. It was a discovery made not through one perfect image, but through repeated observations, careful comparison, and the willingness to investigate a signal that did not immediately fit into a comfortable category. There is something reassuring about that process. Astronomy is often presented through finished pictures and confident labels, but the work usually begins with uncertainty. A point of light dims, a spectral line shifts, a measurement refuses to behave exactly as expected. Researchers check the equipment, gather more data, compare models, and try to find the explanation that survives every test. The universe rarely introduces itself properly. It leaves clues and allows us to do the filing. The catalogue name reflects that practical side of astronomy. EBLM refers to a project studying eclipsing binary systems with low-mass companions. The numbers identify a position in the sky, and the letters describe members of the system. Such names are useful because the sky contains too many objects for all of them to receive memorable titles. Calling every newly measured star something like Harold would create problems surprisingly quickly. EBLM J0555-57Ab may not sound inviting, but it tells astronomers that this object belongs to a specific observed system and distinguishes it from its companions. For listeners, however, the name can remain in the background. The important image is simple. Around 600 light-years away, a star no wider than a large planet moves around a much larger star in less than 8 days. It is difficult to see directly because it is small, cool, and faint. It revealed itself by briefly reducing the light of its companion and by pulling that companion back and forth. Inside the small star, hydrogen nuclei continue to fuse, proving that an object does not need to be broad or brilliant to belong to the stellar population. Its existence also changes the way we think about scale. We tend to arrange space objects by size. Moons are smaller than planets, planets are smaller than stars, and stars are smaller than galaxies. That works as a rough classroom sketch, but reality is less tidy. Some moons are larger than some planets. White dwarfs can contain a mass similar to the Sun in a body roughly the size of Earth. Neutron stars compress more mass than the Sun into a sphere about the size of a city. Giant planets can be wider than the smallest main sequence stars. The category of an object depends on more than its diameter. EBLM J0555-57Ab provides a particularly clear example because it looks, by radius, as though it belongs with the gas giants. If it were drifting alone through space and we could measure only its width, classification would be difficult. Its mass and internal physics tell the real story. Gravity has packed so much material into such a small space that the core can sustain fusion. The star is not a planet that became unusually hot. It is not simply a brown dwarf that received a more flattering label. It is a genuine star operating close to the minimum requirements. Low-mass stars also live very differently from stars like the Sun. They use their hydrogen slowly. Their interiors can transport energy in ways that mix material efficiently, allowing them to draw on a large fraction of their fuel. A star near the bottom of the main sequence can survive far longer than stars with greater masses. Their full life stories cannot yet be observed from beginning to end. These objects use fuel so slowly that the universe has not existed long enough for the smallest of them to complete their natural development. Their distant futures remain predictions based on physics rather than histories astronomers can examine directly. EBLM J0555-57. AB may be tiny, but it is built for patience. That long future stands in contrast to the short orbit we observe. Every few days it completes another trip around its companion. From Earth, each correctly aligned orbit gives astronomers another opportunity to watch the light dip. The rhythm is regular enough to measure, yet the system itself is too distant for any human timescale to affect it. The observations arrive as old light. The calculations are made on modern computers. The object continues on its path, entirely unaware that it has been given a record, a catalogue number, and a growing collection of comparisons with Saturn. You may be wondering what it would look like from nearby. We should be cautious, because direct appearance depends on temperature, atmosphere, wavelength, and the influence of the larger companion. It would not resemble the familiar yellow-white disk of the Sun. A star this low in mass would be much cooler and dimmer, with a large portion of its energy emerging at red and infrared wavelengths. To human eyes, it would be faint compared with the Sun, though faint becomes a flexible word when the object is close enough to damage anything attempting to observe it. Astronomy has many things that are dim from 600 light-years away and deeply impolite from the next seat. The object's small size makes its surface gravity especially striking. Mass pulls inward, and a smaller radius places the visible outer layers closer to the centre of that mass. The result is an intense gravitational field at the surface. This is part of what gives the star its extraordinary density. It contains the material of many Jupiters in a sphere comparable in size to Saturn. The comparison helps us picture its width, but it does not prepare us for the pressure, temperature, and gravity that define its interior. Those interior conditions are central to the larger question behind this entire story. How small can a star actually be? EBLM J0555-57. AB is valuable because it gives astronomers a measured object near the theoretical answer. Models predict a lower mass boundary for sustained hydrogen burning, but the exact limit depends on composition and other physical details. Finding and measuring real systems allows scientists to test those models. A record-sized object is entertaining. A record-sized object that probes the border between two classes of celestial body is scientifically useful. It also matters for the study of planets. Very small stars can make comparatively small planets easier to detect. When an Earth-sized planet passes in front of a tiny star, it blocks a larger fraction of the star's light than it would while crossing a star like the Sun. The planet's gravitational effect may also be easier to measure. Systems around low-mass stars have therefore become important places to search for rocky worlds and to study their atmospheres. Before astronomers can understand those planets, they need accurate knowledge of the stars they orbit. A mistaken stellar radius can lead to a mistaken planetary radius, and a poor estimate of stellar activity can complicate the interpretation of an atmosphere. The small star itself must be understood before its possible planets can be described accurately. In this way, one modest point of light connects several large areas of astronomy. It helps test the physics of the smallest hydrogen-burning stars. It shows how planet surveys can uncover hidden stellar companions. It reminds us that size and identity are not the same thing. It provides another example of an eclipsing system acting as a natural measuring tool. It also prepares us for future discoveries around cool low-mass stars where the difference between a planet, a brown dwarf, and a true star may require more than one kind of observation. For the moment, there is no need to hold all of those ideas at once. Keep only the basic picture. A distant companion passed in front of a brighter star. The dip in light suggested something about the size of a planet. The wobble of the larger star revealed a much heavier object. The final measurements described a body comparable to Saturn in radius, around 85 times the mass of Jupiter, and capable of sustaining hydrogen fusion. That combination placed EBLM J0555-57Ab at the smallest measured end of the stellar family. The first useful thing to know about EBLM J0555-57Ab is that its name contains more information than charm. Astronomers use catalogue names because the sky contains far too many objects for each one to receive a memorable personal title. The letters and numbers help researchers identify the correct location and the correct member of a system without accidentally studying a completely different point of light. This is important when several stars appear close together, which is exactly the situation here. EBLM refers to the project that studied eclipsing binary systems containing very low-mass stellar companions. J0555-57 points toward the object's position in the sky. The capital A identifies the main component of the closer system, while the lowercase b marks the small companion orbiting it. The full arrangement also includes another star labelled B, located much farther from the close pair, so the tiny record holder is not sitting alone in empty space. It belongs to a hierarchical triple system, which is the astronomical term for three objects arranged in two different orbital groupings. That sounds complicated, but the basic layout is manageable. At the centre of our attention is a sun-like star called EBLM J0555-57A. Very close to it is EBLM J0555-57AB, the small star we are meeting tonight. Those two travel around a shared centre of mass in less than 8 days. Farther away is EBLM J0555-57B, another star that appears close to them in the sky and shares their motion through space. The close pair forms the inner system, while the more distant star belongs to the wider arrangement. The entire group is roughly 630 light-years from Earth. A light-year is a measure of distance, not time, although it has a habit of sounding like both. It is the distance light travels in 1 year, which is about 9.46 trillion kilometres. Multiplying that by more than 600 produces a number that is useful to astronomers and almost completely unhelpful when trying to picture the journey. The simpler way to think about it is that the light measured by the Discovery team had been travelling for around 6 centuries. When those photons left the system, no one on Earth had built a modern telescope. The printing press had not yet begun its transformation of European communication. The stars continued their orbits, while human beings developed new instruments, new mathematics, and eventually the ability to notice that one distant point of light became slightly dimmer every 7.757676 days. At that distance, EBLM J0555-57AB cannot be treated like a nearby object that we can photograph in clear detail. It is extremely faint beside its larger companion. The main star contributes most of the visible light, while the little star adds so little that it can easily disappear in the combined signal. This is one reason the object was not introduced to astronomy through a detailed portrait. It became known through measurement. Before considering those measurements, it helps to understand just how small the star is. The Discovery analysis estimated its radius at about 0.84 times the radius of Jupiter. That places it close to the size of Saturn. Depending on which definition of planetary radius is being used, the comparison shifts slightly, because gas giants are not perfect spheres. They rotate, bulge around the equator, and refuse to cooperate with anyone hoping for one simple diameter. The general result remains clear. This star is roughly as wide as Saturn and smaller than Jupiter. That statement sounds wrong only because we are used to placing planets and stars into separate size boxes. In the familiar picture, a planet is a small object circling a much larger star. EBLM J0555-57Ab shows why that picture is useful but incomplete. At the lowest end of the main sequence, a star can occupy less space than a giant planet. Saturn's equatorial diameter is about 120,000 kilometers. EBL J0555-57Ab belongs in that same broad range. Our Sun, by comparison, is nearly 1.4 million kilometers across. If the Sun were reduced to the size of a large exercise ball, the tiny star would be closer to the size of a small orange. The comparison is not exact, and no one should attempt to confirm it by leaving fruit beside gym equipment for several million years. But it gives the correct impression. Width is only one part of the object's identity. The star has a mass of about 0.081 times the mass of the Sun, or roughly 85 times the mass of Jupiter. That enormous amount of material has been compressed into a sphere with a radius comparable to Saturn's. The result is an object far denser than either gas giant. Imagine two containers of nearly the same size. One holds the mass of Saturn. The other holds about 85 Jupiters. The second container would not merely be inconvenient to move, it would produce gravitational conditions that make the word inconvenient seem rather optimistic. This is where the comparison with Saturn has to stop. Saturn is made mostly of hydrogen and helium, as is the small star, but the pressure and temperature inside them are completely different. Saturn's gravity compresses its interior strongly, yet not enough to create the core conditions required for sustained hydrogen fusion. EBLM J0555-57. AB has enough mass for gravity to push its central material to far greater pressure and temperature. Hydrogen nuclei can overcome their electrical repulsion and combine into helium, releasing energy. That reaction is what qualifies the object as a true star. It does not become a star because it is bright enough to look impressive, and it does not lose the title because it is smaller than Jupiter. Stellar classification is based on physical behavior. EBLM J0555-57. AB sustains the fusion process associated with main sequence stars, although it does so at the weakest end of the range. Its estimated surface gravity is around 300 times stronger than the gravity at Earth's surface. Surface gravity describes the acceleration an object would produce near its visible outer boundary. The phrase is slightly misleading for a star because there is no solid ground on which to stand. A star's visible surface is a layer of gas called the photosphere. Trying to land there would be like trying to park on sunlight, except the parking problem would be the least serious part of the attempt. The strong gravity comes from combining substantial mass with a very small radius. Gravity near an object depends on how much mass it contains and how far you are from the centre. Pack more mass into less space, and the gravitational pull at the outer layers becomes stronger. EBLM J0555-57. AB is therefore one of the densest known objects that is not a stellar remnant. That last qualification matters. White dwarfs, neutron stars, and black holes can reach far more extreme densities, but they are the remains of stars that have completed major stages of their evolution. EBLM J0555-57. AB is not a dead core or a collapsed remnant. It is an ordinary hydrogen-burning star, just an unusually small and compact one. The word ordinary may feel inappropriate for an object that caused headlines around the world, but astronomically it belongs to a common family. Low-mass red dwarfs are thought to be the most numerous stars in the galaxy. They are cool, faint, efficient, and difficult to study in detail. A star does not need to be rare in type to be difficult to measure. In fact, the most common residents of the galaxy can remain poorly understood because they contribute so little light. EBLM J0555-57, AB lies at the extreme lower end of that family. Its measured mass is close to the minimum required for sustained hydrogen fusion. The exact boundary is not one perfectly fixed number for every object. Chemical composition influences how a young body contracts, heats, and reaches the conditions needed for fusion. Models place the limits somewhere around 7 to 8% of the Sun's mass, with the details depending partly on metallicity. Astronomers use the term metallicity for the abundance of elements heavier than hydrogen and helium. This includes oxygen, carbon, iron, and many other elements that would not all be called metals in a chemistry classroom. Astronomy adopted its own broad use of the word, possibly because saying everything that is not hydrogen or helium every time would make research papers unnecessarily tiring. The primary star in this system was measured to have a somewhat lower iron abundance than the Sun. The Discovery team found the tiny companion's mass and radius to be consistent with models for a metal-poor, very low-mass star. That agreement mattered because theoretical models become harder to test near the bottom of the main sequence. There are fewer objects with both mass and radius measured accurately enough to provide a strong comparison. Had EBLM J0555-57Ab formed with slightly less mass, it might not have maintained ordinary hydrogen fusion. It would then have belonged among the brown dwarfs. Brown dwarfs form from collapsing gas, much as stars do, but they lack enough mass to sustain the proton-proton fusion process that powers stars such as the Sun. Some can fuse deuterium for a time, and the more massive examples may fuse lithium, but they do not settle into a long main sequence life powered by ordinary hydrogen. The border between a brown dwarf and a very small star is not obvious from size. Brown dwarfs and giant planets can have radii similar to Jupiter. The smallest stars can also have radii similar to Jupiter or Saturn. Over a wide range of mass, adding more material does not always make these objects much wider. That strange behaviour comes from the way matter responds to increasing pressure. A young gas giant or brown dwarf may shrink as it cools. Adding mass increases gravity, which compresses the interior more strongly. The object becomes heavier without expanding in the simple way we might expect. Near the hydrogen burning limit, the mass-radius relation reaches a minimum. EBLM J0555-57Ab sits close to that minimum, where very different amounts of mass can occupy surprisingly similar volumes. It helps to compare three familiar categories. Jupiter has one Jupiter mass and one Jupiter radius. A heavy brown dwarf might have dozens of Jupiter masses while remaining close to Jupiter's radius. EBLM J0555-57 AB has around 85 Jupiter masses and a radius smaller than Jupiter's. Move to more massive main sequence stars, and the radius begins increasing more clearly again. This means a chart of mass against radius does not form one simple rising line. It bends, flattens, and reaches a low point near the boundary between brown dwarfs and stars. Nature has placed the smallest stable stars in a region where the scale on the bathroom scales changes dramatically, while the tape measure seems to have fallen asleep. The tiny radius also tells us something about the star's internal structure. Low-mass stars transport energy differently from the Sun. In the Sun, energy travels outward through a radiative zone and then through a convective outer region. In very low-mass red dwarfs, convection can extend through most or all of the star. Convection moves energy by circulating material. Hotter material rises, releases energy, cools and sinks again. A fully convective star can mix its hydrogen supply throughout much of its interior rather than using only the fuel concentrated near the core. This helps low-mass stars use their fuel with remarkable efficiency. As a result, the smallest stars have extraordinary expected lifetimes. The Sun has a total main sequence lifetime of roughly 10 billion years. A very low-mass red dwarf can remain active for trillions of years, far longer than the current age of the universe. None of these stars has yet had enough time to reach the end predicted by theory. EBLM J0555-57. AB is therefore not a small object in a hurry. Its low luminosity means it consumes hydrogen slowly. Greater stars shine more brightly but spend their fuel faster. The smallest stars take the opposite approach. They produce less light, attract less attention, and continue working for a length of time that makes the lifetime of the Sun appear brief. The discovery paper estimated an age of about 1.9 billion years for the primary star, although the uncertainty was substantial. Because the stars formed as part of the same system, that estimate also gives context for the companion. Even at around 2 billion years old, the small star would still be near the beginning of a life that could continue for an almost unreasonable duration. Its faintness is part of the reason such objects are difficult to observe. A cool red dwarf emits much less visible light than a sun-like star. Beside a brighter companion, it is overwhelmed. The combined point of light mostly tells us about the primary. The smaller star's own spectrum is difficult to isolate, so researchers learn about it indirectly through the effect it has on the system. The larger star, EBLM J0555-57A, has an effective temperature measured at roughly 6,460 Kelvin, making it hotter than the Sun. Its radius was estimated at a little more than the Sun's radius. It is not an enormous giant, but compared with the companion it is broad and bright. When the small star passes across its face, the geometry produces the shallow ellipse that first attracted attention. A third star complicates the view. EBLM J0555-57. B lies about 2.48 arcseconds from the primary as seen from Earth. An arcsecond is 1/3600th of a degree, so this is a very small angular separation. Under ordinary survey conditions, light from A and B can blend together. The researchers compared their motion and radial velocities and concluded that the stars are physically associated, not merely lined up by chance. Their projected separation is hundreds of astronomical units. 1 astronomical unit is the average distance between Earth and the Sun. The distant B component is therefore much farther from the inner pair than the tiny companion is from the primary. Calling the arrangement a triple system may suggest 3 stars moving around one another in a compact group, but the scale is divided. EBLM J0555-57A and AB form a tight pair. The B star occupies a much wider orbit. The result is rather like 2 dancers turning closely together, while a third walks around the outside of the ballroom at a far more relaxed pace. The inner companion's orbit has a semi-major axis of about 0.082 astronomical units. That places it much closer to its primary than Mercury is to the Sun. It completes one orbit in approximately 7.76 days, and the path is slightly eccentric rather than perfectly circular. Because the orbital plane is aligned nearly edge-on from our viewpoint, the small star regularly moves in front of the larger one. That alignment is essential. Most binary systems do not eclipse from Earth, because their orbital planes are tilted differently. We may still detect their motion, but one star never crosses the visible face of the other. Here, chance has provided a particularly useful angle. Each eclipse gives information about relative size, orbital inclination, duration, and geometry. The movement of the primary star gives information about the companion's mass. Combined with models of the larger star, these measurements allow the little object's properties to be calculated with much greater confidence than brightness alone could provide. The system is therefore valuable, not because the tiny star can be viewed easily, but because its arrangement makes it measurable. The companion hides in the primary's glare for most of the orbit, then reveals its outline by blocking a small portion of the light. Its gravity reveals its weight by pulling the primary back and forth. This is also why the object could resemble a planet at first. A transit mainly shows how much of the host's light has been blocked. A Jupiter-sized planet and a Saturn-sized star can cover similar areas of a Sun-like disk. The eclipse depth by itself does not announce whether the companion has 1 Jupiter mass, 10 Jupiter masses, or 85. The name EBLM J0555-57Ab may now feel slightly less like a random string. It identifies a very small member of a close pair inside a wider 3-star system. The object is roughly the size of Saturn, smaller than Jupiter, about 85 times Jupiter's mass, and just heavy enough to sustain the reaction that makes it a star. Those facts describe the object, but they also create the puzzle that first faced the observers. Something with the silhouette of a planet was moving around a sun-like star every few days. The next task was to determine whether the dimming came from the bright primary, whether nearby light had distorted the signal, and whether the hidden companion was a planet, a brown dwarf, or a star. Answering those questions required the researchers to follow the system through repeated eclipses, separate blended sources, and measure a wobble in starlight that no human eye could notice directly. That sequence begins with the movement of the close pair, because before the object's mass could be known, astronomers had to understand the compact orbital dance that kept bringing it across the face of its brighter companion. The close pair does not consist of one star sitting still while the other circles it. That is a useful picture for a first explanation, but it is not what gravity actually produces. EBLM J0555-57A and EBLM J0555-57AB both move. Each one travels around a shared point called the centre of mass, or barycenter. The larger star covers a smaller path, while the tiny companion covers a much wider one, but neither member of the pair is truly stationary. You can see the same principle with 2 people holding hands and turning around each other. If one person is much heavier, the balance point lies closer to them. They make a small circle, while the lighter person travels farther and faster. In the EBLM system, the primary contains a little more than 1 solar mass, while the companion has only about 7% of the primary's mass. The barycenter therefore lies much closer to the larger star, but the larger star still moves enough for astronomers to measure that motion from Earth. The 2 objects complete an orbit every 7.757676 days. That is less time than many people take to answer a message marked "not urgent." During each orbit, the companion travels around the primary at a separation of roughly 0.082 astronomical units. An astronomical unit is the average distance between Earth and the Sun, so the 2 stars are much closer together than Mercury is to the Sun. Mercury orbits at an average distance of about 0.39 astronomical units. The little star is therefore moving through a compact system where the orbital period is measured in days rather than months or years. That closeness is one reason the pair can be studied so effectively. A short orbital period allows astronomers to observe many repeated cycles. Instead of waiting decades for the companion to return to the same position, they can watch it complete another orbit the following week. Each repetition provides another chance to record the change in brightness, measure the movement of the primary, and improve the orbital model. Repetition is extremely valuable in astronomy. A single dip in brightness could come from an instrumental fault, a passing cloud, a fluctuation in the star, or some other source that has nothing to do with an orbiting companion. When the same dip returns at regular intervals, suspicion becomes evidence. When the timing, shape, and duration remain consistent across many observations, the case becomes much stronger. The alignment of this system is particularly helpful. Its orbital inclination is close to 90 degrees from our viewpoint. An inclination of 90 degrees means we are looking almost directly along the plane of the orbit. Because of that angle, the small companion regularly moves across the visible face of the primary star. Most binary systems do not present themselves this conveniently. Their stars may orbit each other perfectly well, but if the orbital plane is tilted toward us at the wrong angle, neither object passes in front of the other. We may detect the pair through changes in position or velocity, yet we do not receive the regular eclipses that reveal their relative sizes. EBLM J0555-57A and its companion happened to be arranged so that the tiny star crosses the primary from our line of sight. During that crossing, it blocks a portion of the primary's light. The primary does not switch off, and the system does not become dramatically dark. The reduction is small. To an unaided observer, nothing would appear to happen at all. The original survey signal showed an observed decrease in brightness of less than half of 1%, although nearby starlight diluted the true eclipse. Once the researchers accounted for that additional light, the calculated eclipse depth was a little over 0.7%. The difference between those values was important because the amount of blocked light helps determine the size of the companion relative to the primary. A reduction of less than 1% may sound unimpressive, but modern photometric surveys are designed to notice changes at that level. They repeatedly measure the brightness of thousands of stars and compare one observation with the next. The result is called a light curve, which is simply a record showing how brightness changes with time. When the companion begins to move in front of the primary, the light curve slopes downward. Astronomers call this stage ingress. Once the companion is fully in front of the stellar disk, the curve reaches its lower section. As the companion leaves the disk, the brightness rises again during egress. The detailed shape contains information about the sizes of the two objects, the speed of the orbit, the angle of the crossing, and the path taken across the primary's face. The crossing is not perfectly centered. The reported impact parameter indicates that the companion travels somewhat away from the exact middle of the primary's disk. It still crosses well within the visible face, producing a clear eclipse rather than merely clipping the edge. That geometry contributes to the final estimates of the stellar radii and the orbital inclination. The event lasts only a few hours. For most of the 7.8-day orbit, the companion is not directly in front of the primary. Then the alignment brings it across the larger star. The light decreases slightly, and a few hours later the system returns to its usual combined brightness. From Earth, the tiny companion does not appear as a small round object moving across a visible stellar surface. The system is far too distant for that kind of direct view. Telescopes record the total incoming light, and astronomers reconstruct the crossing from the change in that light. The orbit becomes visible through a graph rather than a photograph. This is a common feature of modern astronomy. Many important objects are not seen as detailed shapes. They are inferred from patterns. A planet may be known through a repeated transit. A black hole may be detected through the motion of a nearby star. A distant galaxy may reveal its composition through dark lines in a spectrum. The picture in a science article often appears after the measurement, not before it. The eclipse tells us that something with a small radius is crossing the primary. It does not by itself tell us the companion's mass. That creates a problem because planets, brown dwarfs, and low-mass stars can have similar widths. Jupiter is a clear example. It is much less massive than a star, but its radius is larger than that of EBLM J0555-57Ab. A transit caused by a Jupiter-sized planet and one caused by a tiny star can therefore look remarkably similar. Both companions can block roughly the same fraction of a Sun-like star's visible surface. This overlap is one reason small stars can hide inside planet surveys. The survey detects the silhouette, not the internal physics. It measures how much light is missing and how often the event returns. Until additional observations are made, a stellar companion may continue wearing a very convincing planetary disguise. The larger star's motion removes that disguise, as EBLM J0555-57Ab travels around the barycenter. Its gravity pulls the primary from one side of its small orbit to the other. Sometimes the primary is moving partly toward Earth. Half an orbit later, it is moving partly away. Astronomers detect this through the light spectrum. When the primary moves toward us, its spectral lines shift toward shorter wavelengths. When it moves away, those lines shift toward longer wavelengths. This is the Doppler effect, the same general principle that changes the pitch of a passing siren, although no one has yet reported hearing a star go past with its alarm on. The primary's measured radial velocity semi-amplitude was about 7.74 kilometers per second. That is far larger than the subtle wobble usually caused by a planet similar to Jupiter. The size of the motion immediately indicated that the companion had substantial mass. It was not simply a gas giant moving close to the star. A massive companion pulls strongly on its primary. A low-mass planet produces a smaller response. The relationship is not determined by the companion alone, because the primary's mass, the orbital period, the orbital inclination, and the eccentricity also matter. Once those quantities are included, the radial velocity curve provides what astronomers call a mass function. The mass function does not instantly provide one final number without any assumptions. Researchers still need an estimate of the primary star's mass. They obtain that by studying its temperature, chemical composition, density, spectrum, and agreement with stellar evolution models. Once the primary is characterized, the orbital measurements can be used to calculate the companion's mass. For EBLM J0555-57Ab, the resulting estimate was about 85 Jupiter masses, with an uncertainty of a few Jupiter masses. Its mass ratio relative to the primary was approximately 0.072. Those values placed it well beyond the ordinary planetary range and close to the lower boundary for sustained hydrogen fusion. The eclipse and the radial velocity wobble therefore answered different questions. The eclipse measured the companion size relative to the primary. The wobble measured the gravitational effect of the companion and helped reveal its mass. Either signal alone would leave important uncertainty. Together they described a very small but very heavy body. This is why eclipsing binaries are so useful. They act as natural laboratories for stellar measurement. When the orbital angle is known and the two objects repeatedly pass through useful positions, astronomers can determine properties that are much harder to obtain for isolated stars. An isolated, faint red dwarf may reveal its temperature and brightness, but its mass and radius often depend heavily on theoretical models. In an eclipsing binary, orbital mechanics provides a more direct route. Gravity produces measurable motion, while the eclipse provides measurable geometry. The EBLM project was created to make use of systems like these. Planet surveys had already collected enormous amounts of brightness data. Among their candidates were objects that looked like transiting gas giants, but were actually low-mass stars. Instead of treating every false planetary signal as useless, researchers recognized that the imposters could provide an excellent sample for studying the lowest mass stars. That change in perspective is worth pausing over. A survey can begin with one goal and produce valuable discoveries in another area. The equipment does not become offended when it finds the wrong category of object. A candidate that fails to become a planet may still become an important star. The term false positive can sound as though the observation was a mistake. Usually the signal itself is real. The mistake would be assuming too early that only one explanation is possible. In this case, the repeated reduction in light genuinely came from an orbiting body crossing a star. The question was whether that body was a planet, a brown dwarf, or another star. The orbit was not completely circular. The reported eccentricity was about 0.089, which means the path is slightly elongated. A perfectly circular orbit has an eccentricity of 0. Values closer to 1 represent increasingly stretched ellipses, though bound planetary and stellar orbits remain below 1. An eccentricity of 0.089 is small, but the measurements indicated that it was significant. The separation between the two stars therefore changes somewhat during each orbit. At one part of the path, the companion is closer to the primary. At another, it is farther away. Close binary systems often become more circular over time because tidal interactions redistribute energy. Each star raises a gravitational distortion in the other, and those repeated distortions can gradually alter the orbit and rotation. Since this pair is close and has a period under 8 days, its remaining eccentricity attracted attention. The discovery paper suggested that the wider third star, EBLM J0555-57B, may have influenced the earlier orbital history of the close pair. In some hierarchical triple systems, a distant companion can change the eccentricity and inclination of an inner orbit through a process known as Kozai-Leadoff oscillations. Tidal friction can then shrink and reshape the inner orbit. The researchers presented this as one possible explanation rather than a settled history. The system we see today may therefore be the result of long gravitational interactions among three stars. The distant component moves around the inner pair at a projected separation of hundreds of astronomical units. Its orbit would be vastly slower than the 7.8-day motion of the close companion, but even a distant object can influence a system over long periods. That influence should not be imagined as a sudden shove. Orbital changes in hierarchical systems can accumulate through repeated gravitational effects. The outer star may slowly alter the geometry of the inner orbit, while tides become important whenever the inner objects pass especially close together. At the present separation, other effects, including relativistic precession, may suppress strong Kozai-Leadoff cycles. The paper therefore did not claim that the wide companion is currently driving dramatic changes. It noted that such interactions may have mattered earlier, when the inner orbit could have had a different shape or separation. This gives the small star two useful identities. It is an object near the hydrogen burning limit, and it is also part of a compact orbital system with a potentially complicated past. Its physical size tells us about the behaviour of matter at very low stellar masses. Its orbit tells us about gravitational measurement and the evolution of multiple star systems. The larger primary affects the companion in ways beyond simple orbital motion. At such a close distance, the small star receives far more external radiation than an isolated red dwarf would. Its near side is continually exposed to the primary's light, and tidal forces may influence its rotation. Many close companions become tidally locked, meaning their rotation period matches their orbital period, and the same side tends to face the primary. The available measurements for EBLM J0555-57Ab do not directly provide a complete map of its rotational surface, so it is better not to state that locking as a confirmed fact. The short orbit makes tidal interaction relevant, but the exact rotational condition requires evidence. That distinction between expectation and measurement is important. Astronomy often uses models to predict what is likely, but a likely state is not automatically an observed state. A careful description separates what the data show from what physical reasoning suggests. The data clearly show a repeated eclipse, a short period, a nearly edge-on orbit, a measurable eccentricity, and a strong radial velocity signal from the primary. They support a companion with stellar mass and a radius comparable to Saturn. They also reveal the presence of a wider third star associated with the system. What they do not provide is a detailed image of the small star's surface. We do not see cloud bands, spots, or glowing structures in a resolved disk. The companion remains hidden within the combined light of the system except through its effects. Its own visible contribution is tiny. The brighter primary dominates the spectrum, which is why the system is described as a single-lined spectroscopic binary. Astronomers clearly observe the primary's spectral lines moving back and forth, while the companion's lines are too faint to stand out cleanly. A double-line binary is easier in one respect because both sets of spectral lines can be tracked. Each star announces its motion directly. In a single-line system, only one voice is clear, and the properties of the hidden member must be reconstructed from the visible star's response. This reconstruction becomes more difficult when another source contributes light. EBLM J0555-57B appears only about 2.48 arc seconds from the primary in the sky. Depending on the telescope, atmospheric conditions and observing aperture, some of its light can enter the same measurement. That extra light makes the eclipse appear shallower. Suppose one lamp dims slightly, while a second lamp nearby remains constant. If a detector records both lamps together, the total change looks smaller than the true change in the first lamp. The companion has not blocked less light. The unaffected source has diluted the measurement. The researchers therefore had to establish which star was actually being eclipsed and how much contaminating light came from the neighbour. They compared measurements taken with different apertures and obtained focused images that separated the A and B components more clearly. A smaller aperture centered on the brighter A component produced a deeper eclipse signal than a larger aperture containing both stars. That result identified A as the source of the eclipse. The team then calculated a dilution correction for the light contributed by B. Without that correction, the companion's radius would have been underestimated. The same nearby star could also contaminate spectra. Changing atmospheric seeing conditions altered how much of B's light entered the spectrograph's fibre. The team examined the shapes of the cross-correlation functions used to measure radial velocity and rejected contaminated observations where necessary. This is the less glamorous part of finding a record-sized star, but it is essential. The final numbers depend on understanding where the light came from, which measurements were clean, and how the instrument responded under different conditions. A remarkable conclusion can rest on several very ordinary decisions about apertures, fibres, noise, and whether one data point should be trusted. The tiny companion remained hidden, not because it was doing nothing, but because almost everything it did had to be inferred through another star. It blocked the primary's light. It pulled the primary through a small orbit. It altered a graph rather than producing a clear image of itself. Once astronomers combined those effects, the supposed planet-sized candidate became a stellar object with extraordinary density. The orbital motion established that the small silhouette belonged to something far heavier than a planet. The eclipse established that all of that mass occupied a volume comparable to Saturn's. The pair's binary motion was therefore not merely an interesting detail about where the star lives. It was the measuring device that made the discovery possible. Without the alignment, there would have been no eclipse. Without the close orbit, repeated events would have been slower to collect. Without the companion's gravitational pull on the primary, its stellar mass could have remained hidden behind its planetary size. The next step is to follow the observations in the order they were gathered. Thousands of survey measurements, 17 transit-like signals, high-resolution spectra, follow-up eclipses, and the careful removal of light from the neighbouring star. That process shows how astronomers can begin with a small dip in brightness and finish with the measured mass and radius of a star that is almost small enough not to be a star at all. That sequence began with a telescope survey that was not looking for the smallest star in the universe. It was looking for planets. The project was called WASP, the Wide-Angle Search for Planets. Its purpose was to monitor large areas of the sky and look for stars that became slightly dimmer at regular intervals. A repeated dip can be the sign of a planet passing in front of its host star. The planet blocks a small fraction of the light, moves on through its orbit, and later returns to produce the same pattern again. This method sounds simple when described in one sentence. In practice, it requires thousands of measurements, careful comparison, and a great deal of patience with weather, instruments, and stars that sometimes change brightness for reasons of their own. A telescope does not see a tiny black circle moving across a large glowing disk. It records points of light and measures whether those points are a little brighter or a little fainter than they were before. WASP-South observed the source now called EBLM J0555-57 between September 2008 and March 2012. Over 4 observing seasons, the survey collected 34,091 brightness measurements. A search algorithm then examined those measurements for repeating patterns and identified 17 transit-like events occurring every 7.7576 days. 17 dips do not yet tell you what caused them. They tell you that something regular is happening. The timing suggested an orbiting companion, and the shallow depth made that companion look small compared with the visible star. From the survey data alone, a large planet was a perfectly reasonable possibility. This is how many hot Jupiters are first noticed. A hot Jupiter is a gas giant orbiting very close to its star. Because the orbit is tight, the planet crosses the star frequently. Because the planet is large, the reduction in brightness can be detected by ground-based surveys. A period of under 8 days and a shallow eclipse fit the general shape of that familiar discovery. The object was therefore useful enough to investigate, but not yet unusual enough to announce. Planet surveys produce many candidates, and a candidate is only the beginning of the process. Some turn out to be planets. Others are eclipsing binary stars, blended systems, variable stars, or signals produced by the equipment in the atmosphere. Astronomers sometimes call these non-planetary cases false positives. The phrase can sound as though nothing was there, but that is often not true. The dip may be completely real. What changes is the explanation. A star crossing another star can imitate the shadow of a planet. Two unrelated stars can overlap in the same patch of sky and confuse a measurement. A faint eclipsing binary can sit behind a brighter star, making a deep stellar eclipse appear shallow once all the light is blended together. This possibility had to be taken seriously for EBLM J0555-57, because another star was visible only a few arcseconds from the main target. At first, the WASP images did not cleanly separate all of the light. The survey cameras were designed to watch broad regions of sky, not to produce a close portrait of every source. The measured brightness therefore included light from more than one star. Think of watching two lamps through a window from far down the street. One lamp dims but the other remains steady. If you cannot separate them, the total light changes by less than the true change in the first lamp. The steady lamp fills in part of the missing brightness. An eclipse that is actually fairly clear can look weaker and more planet-like. The nearby source became known as EBLM J0555-57B. Before the team could determine the size of the transiting object, they needed to know whether the dip came from the brighter star or from the nearby B star. If the wrong star was identified as the source, every later estimate would be built on the wrong geometry. Follow-up observations were made with telescopes capable of seeing the pair more clearly. The researchers compared brightness measurements made with two different apertures. A large aperture included light from both A and B. A smaller aperture was centered more tightly on A and reduced the contribution from B. The eclipse appeared deeper in the smaller aperture. That result identified A as the star being crossed. Removing more of B's constant light made the true dimming easier to see. The companion was not passing in front of the neighbouring star. It was orbiting the brighter primary. Focused images later measured the separation between A and B at about 2.48 arcseconds. The team also measured how much fainter B was in several colour bands. Those measurements allowed them to calculate the dilution of the eclipse and correct for it in the final model. The correction mattered. Without it, the companion would appear smaller than it really was. Transit depth is closely related to the area ratio of the two disks. If a companion blocks 1% of a star's light, it has roughly 1/10 of the star's radius. Assuming a simple central crossing and ignoring several details that astronomers do not have the luxury of ignoring, add extra light from a third object, and the observed dip becomes shallower. The radius estimate then shrinks unless the contamination is included. In this system, the nearby star diluted the measured eclipse depth by a factor of about 1.5. Correcting that factor was one of the steps that turned a rough survey signal into a useful physical measurement. The team also had to establish whether A and B were actually related. Two stars can appear close together simply because they lie along the same line of sight. One may be nearby and the other much farther away, creating a chance alignment with no shared orbit. Their velocities and motion across the sky showed that A and B were associated. They had nearly matching systemic radial velocities and shared proper motion. This supported the conclusion that the visible pair and the tiny transiting companion form a hierarchical triple system. That wider arrangement complicated the observations, but it also provided useful context. A was the bright star being eclipsed. Ab was the hidden close companion. B was the more distant stellar neighbour adding unwanted light and requiring the researchers to check everything twice, which is a role that many neighbours perform without needing to be hundreds of astronomical units away. Once the source of the eclipse had been identified, attention shifted to the companion's mass. A transit tells astronomers how much area the companion covers. It does not tell them whether the object is light or heavy. A large planet and a very small star can cast shadows of almost the same size. The team used the Corelli spectrograph, mounted on the Swiss Euler telescope in Chile, to measure the motion of EBLM J0555-57A. Between November 2013 and January 2017, they collected 30 spectra of the primary. A spectrum spreads starlight into its component wavelengths. It contains absorption lines produced by elements in the star's atmosphere. Those lines act as markers. When the star moves toward Earth, the markers shift slightly toward shorter wavelengths. When the star moves away, they shift toward the longer wavelengths. The shift is extremely small, but high-resolution spectrographs can measure it. By observing at different points in the orbit, astronomers build a radial velocity curve showing how quickly the visible star moves toward and away from us. A planet causes its host star to wobble. A second star causes a wobble as well, usually a much larger one. The important question is not whether the primary moves, but how much it moves, and how that movement matches the period of the eclipse. In this case, the motion was too large to be caused by an ordinary planet. The radial velocity semi-amplitude was about 7.7 kilometers per second. That meant the hidden companion was pulling hard on the primary. The object casting the planet-sized shadow had a stellar amount of mass. At this point, the candidate stopped being a normal exoplanet candidate. It became an eclipsing low-mass companion. The survey had found something that looked like a hot Jupiter from its width, but behaved like a star through gravity. That combination was exactly what the EBLM project was designed to study. EBLM stands for Eclipsing Binaries with Low-Mass Companions. Planet surveys such as WASP had already discovered many transit signals. Some of those signals were produced by low-mass stars passing in front of larger stars. Rather than discarding them as failed planets, the EBLM team used them to investigate the poorly measured lower end of the stellar main sequence. This is a useful example of scientific equipment finding more than it was built to find. A planet survey watches for shadows. Shadows do not arrive with labels. The same data can reveal planets, brown dwarfs, and stars, provided the follow-up work is able to measure the differences. The radial velocity analysis was not completely straightforward because the nearby B star could also contaminate the spectra. Corelli gathered light through a fibre. Changes in atmospheric seeing affected how much of B's light entered that fibre along with light from A. When more light from B entered, the combined spectral profile changed. The researchers examined the width of the cross-correlation function used to measure radial velocity. In simpler terms, they checked whether the shape of the spectral signal looked like the clean primary, or like a mixture of two stars. They separated the measurements into clean and contaminated groups using a statistical model. Spectra that were very unlikely to belong to the clean group were rejected, and one additional point with an unusual line-shape measurement was excluded. 18 uncontaminated spectra were then combined to study the primary star's atmosphere. This careful filtering may sound less exciting than discovering the smallest measured star, but the exciting conclusion depends on it. A contaminated spectrum can shift the apparent velocity. A shifted velocity changes the inferred orbit. The orbit affects the calculated companion mass. Leaving a doubtful data point in the analysis because it looks interesting, is a reliable way to make an interesting mistake. From the clean spectra, the team estimated the primary's temperature, surface gravity, rotation, and ion abundance. The effective temperature was about 6,461 Kelvin, making the primary somewhat hotter than the Sun. Its ion abundance was lower than the Sun's, and its properties were consistent with a star a little more massive and larger than our own. These primary star measurements were essential because the companion's mass could not be calculated in isolation. The radial velocity curve provides a mass function, which relates the two masses, the orbital inclination and the measured motion. To turn that relationship into the mass of AB, the team needed an estimate of A's mass. The eclipse geometry helped determine the primary's density. Stellar evolution models then helped estimate its mass. The researchers refined the result iteratively, passing information between the transit model, the velocity model, and the stellar model until the values were mutually consistent. Additional eclipse observations improved the shape of the light curve. The Euler telescope observed an eclipse in February 2014, and the TRAPPIST telescope observed another in December 2015. Both observations were made in a near-infrared filter called Z'. Near-infrared observations were useful because cool low-mass objects contribute relatively more light at longer wavelengths, although the small companion still remained difficult to detect directly. The main purpose here was to obtain cleaner, higher-quality eclipse curves than the original broad survey could provide. These follow-up curves allowed the team to examine the ingress, the flat or rounded lower portion, and the egress in more detail. The duration and shape constrained the impact parameter, which describes how far from the centre of the primary the companion crosses. They also help determine the ratio between the two radii. Real observing nights are rarely as neat as the diagrams. The background light changed during both eclipse sequences. One observation had limited coverage after the companion had finished crossing. The TRAPPIST telescope also performed a meridian flip, a normal change in orientation required by its mounting as the target moved across the sky. That flip could introduce a small offset in the measured brightness. The researchers included these effects in the model rather than pretending. The data had been collected under ideal conditions. They tested different ways of removing background trends, added an offset for measurements made before and after the telescope flip, and enlarged the quoted uncertainties to account for correlated noise. Correlated noise means neighbouring measurements can share the same disturbance. A passing atmospheric condition or a slow instrumental change may affect several points in a row. If those points are treated as fully independent, the result can look more precise than it really is. To prevent that, the team examined the residuals after fitting the light curves. They grouped the residuals over intervals of 10 to 30 minutes and compared the scatter with what would be expected from uncorrelated noise. The uncertainties were then increased, particularly for the TRAPPIST observations. This did not weaken the discovery. It made the reported confidence more realistic. Good measurement is not about producing the smallest possible error bars. It is about producing error bars that honestly describe what the observations can support. The final analysis combined the follow-up light curves with the radial velocities in one global model. The researchers used a binary star light curve code to calculate how the system should appear for different radii, orbital angles, eccentricities, and velocities. A Markov chain Monte Carlo method explored the possible parameter values. The name sounds like a casino designed by mathematicians, but the basic idea is manageable. The algorithm tries many combinations, compares each one with the data, and spends more time in regions where the model fits well. The resulting distribution shows not only the most likely values, but also the range of uncertainty around them. The fitted quantities included the orbital period, the time of mid-eclipse, the observed eclipse depth, the duration, the impact parameter, the radial velocity amplitude, the eccentricity, and the system's overall velocity. The dilution from star B was included so the model could recover the true eclipse depth. The analysis also accounted for an upgrade to the Corelli spectrograph that changed its velocity 0 point. Data taken before and after the upgrade were allowed to have separate reference velocities. The orbit remained the same, but the instrument's baseline had shifted slightly. Step by step, the candidate's identity became harder to mistake. WASP supplied the repeated timing. The focused images identified the eclipse star and measured the contaminating neighbour. Coralie revealed the primary's strong wobble. Euler and Trappist recorded cleaner eclipse shapes. Spectral analysis described the primary. The joint model brought all of the information together. The resulting companion mass was about 85 Jupiter masses, or 0.081 times the mass of the Sun. Its radius was about 0.84 Jupiter radii, comparable to Saturn. Its surface gravity was among the highest measured for an object that was not a collapsed stellar remnant. Nothing in the first shallow dip had announced those final properties. A transit-like signal only said that an object of a certain apparent width was crossing a star at regular intervals. The hidden mass had to be uncovered through gravity. That is why the discovery was both accidental and deliberate. WASP was not specifically searching for a Saturn-sized star, so the object was accidental in relation to the survey's original goal. Once the candidate appeared, however, the conclusion required years of deliberate follow-up. The team did not simply notice an unusual dip and guess correctly. They tested each possible source of confusion until the planet-sized silhouette and the stellar mass belonged to the same object. By the time the study was published in 2017, EBLM J0555-57Ab had moved from a row of survey measurements to a place near the minimum of the observed stellar mass-radius relation. It had been found by equipment meant for planets because in radius alone it could pass for one. What remained was to understand. How did the observations produce the two numbers that made the results so important? How was a radius measured from a diluted eclipse and a mass inferred from the motion of another star? Turning changes in light and velocity into a physical scale sounds straightforward once the final numbers are printed in a table. The companion has a certain radius, a certain mass, and a certain surface gravity. Everything appears settled. Reaching those numbers, however, required astronomers to combine several measurements that did not describe the small star directly. No telescope resolved EBLM J0555-57Ab as a separate round disk. Researchers could not point at the image, measure its width, and compare it with Saturn. From nearly 200 parsecs away, the entire close pair appeared as one source of light, with additional light arriving from the wider third star nearby. The size of the companion had to be calculated from the eclipse. Its mass had to be calculated from the primary star's motion. The dimensions of the primary also had to be estimated because measuring the companion as a fraction of another star is only useful when the size of that other star is known. It is similar to seeing a small object pass in front of a distant lamp. You can work out what fraction of the lamp it covers, but that does not immediately tell you whether the object is the size of a coin or the size of a dinner plate. You first need to know the actual dimensions of the lamp. The eclipse provided a ratio. The radial velocity measurements provided a gravitational relationship. Spectroscopy described the primary star. Stellar models supplied an estimate of its mass. The researchers then fitted all of these pieces together until one set of physical values explained the observations. The starting point was the light curve. During an eclipse, the small companion covers part of the visible surface of the primary. If both objects were perfectly dark-edged circles with uniform brightness, the calculation would be simple. The fraction of light removed would be roughly equal to the area of the companion divided by the area of the primary. Areas depend on radius squared. A companion with 1/10 of the primary's radius covers roughly 1/100th of its visible area. It would therefore block around 1% of the light during a central crossing. Real stars make the situation less tidy. Their surfaces do not have uniform brightness. The center of a stellar disk looks brighter than the edge, an effect called limb darkening. Near the visible edge, we are looking through cooler, higher layers of the atmosphere. Near the center, we see deeper into hotter material. A companion crossing the centre of a star therefore blocks more light than the same companion crossing close to the edge. Astronomers must account for the path of the eclipse as well as the size of the object. The path is described partly by the impact parameter. An impact parameter of 0 would mean the companion crosses directly through the centre of the primary's visible disk. A larger value describes a path closer to the edge. For EBLM J0555-57Ab, the estimated impact parameter was around 0.35, although the uncertainty was fairly broad. The companion crossed away from the exact centre, but not so close to the edge that the eclipse became merely a grazing event. The orbital inclination was measured at nearly 90 degrees. This confirmed that the system is viewed almost edge-on. A slightly different angle would still allow the stars to orbit in exactly the same way, but the companion might pass above or below the primary from our perspective, leaving no eclipse for us to measure. The observed eclipse depth was about 0.00474. In percentage terms, the combined light dropped by roughly 0.47%. That was not the true fraction of the primary's light being blocked, because the observed signal contained extra light from EBLM J0555-57B. The wider star remained steady during the close pair's eclipse. Its light filled in part of the dip, much as an unaffected lamp can make the dimming of a neighbouring lamp appear less severe. Focused images showed that the B component was separated from A by about 2.48 arc seconds. The researchers measured the difference in brightness between the two stars in several filters. In the near-infrared filter used for the detailed eclipse observations, they calculated that the extra light diluted the eclipse depth by a factor of about 1.5. After correcting for that contamination, the calculated eclipse depth was about 0.00713, or a little over 0.7%. That correction increased the inferred size of the companion. Without it, the object would have appeared to cover less of the primary. The resulting radius would have been too small, and the record might have looked even more dramatic while being less accurate. Astronomy occasionally requires making a result slightly less exciting in order to make it true. The corrected light curve gave a radius ratio of about 0.0844. In other words, the companion's radius was approximately 8.4% of the primary star's radius. That was still only a ratio. To convert it into kilometres, Jupiter radii or solar radii, the researchers needed the radius of EBLM J0555-57A. The primary was examined through spectroscopy. Its light was separated into many wavelengths, revealing absorption lines from elements in its atmosphere. The strengths and shapes of those lines provided estimates of effective temperature, ion abundance, surface gravity, and rotational broadening. Its effective temperature was measured at about 6,461 Kelvin, making it hotter than the Sun. Its ion abundance was somewhat lower than the Sun's, with a reported value of roughly minus 0.24 dex. The word dex describes a logarithmic difference. A value below 0 indicates a lower abundance than the Sun. It is a compact way for astronomers to discuss chemical composition without repeatedly saying that one star contains a certain fraction of another star's iron relative to hydrogen. The team also used the density of the primary derived from the eclipse geometry. This may seem surprising, because an eclipse does not place the star on a set of scales. It does, however, reveal how the stellar size relates to the orbit. The duration of the eclipse depends on the size of the primary, the size of the companion, the speed of the crossing, the angle of the orbit, and the distance between the two objects. The orbital period was already known very precisely. The radial velocity data constrained the orbital shape and speed. Combining these quantities allowed the primary's mean density to be estimated. The calculated density was about 1.16 times the Sun's density, although the uncertainty extended farther toward lower values than higher ones. That density, together with the measured temperature and chemical composition, could be compared with models showing how stars of different masses and ages are expected to behave. The researchers used a program called beige mass for this step. It compared the observed properties of the primary with stellar evolution calculations and estimated a primary mass of about 1.13 solar masses. The process was iterative. An initial density from the eclipse was used to estimate the primary's mass. That mass was then placed back into the orbital and eclipse calculations to refine the density. The updated value could be returned to the stellar model. In this case, the estimates were already consistent after the first iteration. The numbers did not have to be chased around the computer for days while everyone reconsidered their career choices. Once the primary's radius had been established at approximately 0.99 solar radii, the radius ratio could be converted into the physical radius of the companion. The result was about 0.084 solar radii. Expressed using Jupiter as the reference, EBLM J0555-57Ab had a radius of about 0.84 Jupiter radii. The upper uncertainty was around 0.14 Jupiter radii, while the lower uncertainty was about 0.04. The uneven uncertainty is important. It means the likely range did not extend equally in both directions. The best fitting value was 0.84 Jupiter radii, but the data allowed more room for the star to be larger than for it to be smaller. This wider upper uncertainty came partly from limitations in the eclipse observations. The researchers had only 2 detailed follow-up light curves, and those observations were affected by changing backgrounds, correlated noise, incomplete out-of-eclipse coverage, and the need to correct for the nearby star. A better light curve would sharpen the measurement of the ingress and egress. It would make the impact parameter clearer, constrain the primary's radius relative to the orbit, and reduce the range of possible companion sizes. Ingress is the period when the companion begins crossing the stellar disk. Egress is when it leaves. The time taken for those stages helps reveal the companion's width. A large companion takes longer to move fully onto the disk than a small companion travelling at the same speed. A path near the edge also produces a different duration from a path near the centre. That is why the exact shape of the eclipse matters more than the lowest point alone. The Euler and TRAPPIST measurements had to be corrected for slow changes in brightness that were not caused by the eclipse. Atmospheric conditions, background light, image position, and the width of the stellar image could all affect the recorded flux. The researchers tested several baseline models and compared them using the Bayesian information criterion. This method rewards a model for fitting the data well, but penalizes it for using unnecessary complexity. Without such a penalty, it is always possible to improve a fit by adding more adjustable terms. Eventually the model becomes excellent at reproducing every irregularity in one dataset, while becoming useless for describing anything else. It is the scientific equivalent of solving a loose floorboard by rebuilding the entire house around it. The TRAPPIST observation also included a meridian flip. As the telescope tracked the star across the sky, its mount had to rotate to continue following the target. That changed the orientation of the field on the detector and could create a small shift in the measured brightness. An offset parameter was included so measurements made before and after the flip could be joined without assuming the equipment had behaved identically on both sides. After fitting the observations, the team examined the remaining scatter. If each measurement had contained purely random noise, averaging several nearby points would reduce that scatter in a predictable way. Instead, atmospheric and instrumental effects can influence a series of measurements together. This is called correlated noise, or red noise. The points are not fully independent. A small drift may remain for 10 or 20 minutes, making several consecutive measurements too bright or too faint. The light curves were grouped over intervals from 10 to 30 minutes. The observed scatter in those groups was compared with the scatter expected from independent noise. The uncertainties were then increased by a factor of 2.02 for the TRAPPIST data and 1.37 for the Euler data. Increasing an uncertainty can feel like admitting defeat, but it is the responsible response when the measurements contain more noise than the initial error estimates describe. The purpose of an uncertainty is not to make the result look precise. It is to show how precisely the result is actually known. While the eclipse revealed the radius ratio, the mass came mainly from radial velocity. Corelli measured how quickly the primary moved toward and away from Earth as the two stars orbited their barycenter. The velocity curve had a semi-amplitude of about 7.740 km per second. Semi-amplitude means the size of the movement, from the system's average velocity to one extreme of the curve. The full difference between the most positive and most negative orbital velocities was therefore roughly twice that value. From the orbital period, eccentricity, inclination, and radial velocity amplitude, the researchers calculated the binary mass function. This quantity combines the companion's mass with the primary's mass in a relationship dictated by orbital mechanics. The measured mass function was approximately 0.0003686 solar masses. The number looks small because of how the mathematical expression is constructed. It does not mean the companion itself had only a tiny fraction of a solar mass function lying around somewhere in the orbit. To obtain the companion's actual mass, the mass function was combined with the estimated mass of the primary and the nearly edge-on inclination. The result was about 85.2 Jupiter masses, or 0.0813 solar masses. The upper uncertainty was about 4 Jupiter masses, while the lower uncertainty was just under 4. This placed the object near the lower boundary, where sustained hydrogen fusion becomes possible. The resulting mass ratio was about 0.072. The companion contained only a little more than 7% of the primary's mass. Even so, it produced a much larger radial velocity signal than a typical planet because 7% of a solar mass is still an enormous amount of material. Another useful quantity could be derived with less dependence on the uncertain primary mass. The companion's surface gravity was calculated directly from the orbital and eclipse parameters. Surface gravity depends on mass divided by radius squared. Normally, finding it would require separate measurements of mass and radius. In an eclipsing system with radial velocity data, however, the equations can be rearranged so the companion's surface gravity is obtained from the observable orbital quantities. The reported value was a logarithmic surface gravity of about 5.50 in centimeter-gram-second units. Converting that into a more familiar comparison gives a gravitational acceleration around 300 times stronger than Earth's. This quantity was especially robust because it did not rely strongly on the assumed primary mass. Even if the stellar model for the larger star changed slightly, the companion would still be recognized as an object with extreme surface gravity. The density estimate was similarly remarkable. Using the measured mass and radius, the team calculated a mean density of about 188 grams per cubic centimeter, with a broad uncertainty range. Earth's average density is about 5.5 grams per cubic centimeter. Water is about 1 gram per cubic centimeter. The small star's average value was therefore dozens of times greater than Earth's, and nearly 200 times the density of water. That does not mean every layer has the same density. Like other stars, EBLM J0555-57Ab becomes much denser toward its center. The quoted number is the average obtained by dividing the total mass by the total volume. Because volume depends on radius cubed, uncertainty in the radius has a strong effect on calculated density. A modest increase in radius produces a much larger increase in volume and a lower average density. This is another reason accurate eclipse photometry matters. All of the reported quantities were produced through a Markov chain Monte Carlo analysis. Instead of finding one single best fit and stopping, the method explored a large range of possible parameter combinations. The researchers ran 100 chains with 10,000 steps each. At every stage, the algorithm considered a possible set of values for the orbit, eclipse, velocity curve, and instrumental corrections. Combinations that matched the data well received greater statistical support. The resulting collection formed posterior probability distributions. These distributions showed which values were most likely and how strongly the different parameters were connected. For example, A slightly larger primary radius could allow a larger companion radius while preserving nearly the same radius ratio. A different impact parameter could alter the inferred geometry and change the range of allowed radii. A shift in the primary mass would affect the calculated companion mass. The final uncertainty therefore included more than the visible scatter of individual measurements. It reflected the way multiple unknown quantities influence one another. The researchers also tested whether a disagreement in the primary star's spectroscopic surface gravity affected the result. Surface gravity measured directly from stellar spectra is often poorly constrained. The spectroscopic value for the primary differed from the value calculated using its modelled mass and radius. When the team repeated the analysis using the calculated gravity as a prior for the spectral fitting, the resulting primary and companion properties remained consistent with the original estimates. The small star did not disappear when one uncertain measurement was treated differently. No individual observation was enough to establish the result. The WASP survey determined the repeated period. Follow-up photometry measured the eclipse shape. Focused imaging revealed the contaminating third star. Spectroscopy described the primary's atmosphere. Radial velocity measured its orbital wobble. Stellar models estimated its mass. A global statistical fit linked everything together. The outcome was not a perfectly exact radius. The star could plausibly be somewhat larger than the central value, and the discovery team specifically noted that higher precision photometry could improve the measurement. Even with that uncertainty, the object occupied the lowest region of the measured stellar mass radius diagram. Its most likely radius was smaller than Jupiter's and comparable to Saturn's, while its mass was firmly within the stellar range predicted for its chemical composition. This is how astronomers measure something that is small, faint, blended with other light, and hundreds of light years away. They do not rely on one view. They allow the orbit to provide a ruler and gravity to provide a scale. Each eclipse reports how the objects compare in width. Each spectral shift reports how strongly they pull on one another. Models of the primary turn ratios into physical units. Statistical analysis keeps track of the uncertainty instead of hiding it. Once those measurements are assembled, the small point of light is no longer defined only by a shallow dip. It becomes an object with about 85 Jupiter masses compressed into a body narrower than Jupiter. And that combination leads directly to the next question. What happens when so much matter is forced into so little space, while the object remains an ordinary hydrogen-burning star? The result is not simply a heavier version of a gas giant. It is a body with intense gravity, enormous internal pressure, and a core hot enough to sustain the process that separates stars from brown dwarfs. The word weight is being used loosely here. In physics, mass is the amount of matter an object contains, while weight is the force produced when gravity acts on that mass. EBLM J0555-57. AB has a mass of about 0.081 times the mass of the Sun. Expressed in planetary units, that is approximately 85 times the mass of Jupiter. Its radius is only about 0.84 times Jupiter's radius. That means a large amount of matter has been packed into a surprisingly small volume. The comparison with Saturn helps us imagine the width, but it does not help much with the internal conditions. Saturn and this star may be similar in size, yet they belong to completely different physical regimes. Saturn contains roughly 95 times the mass of Earth. EBLM J0555-57Ab contains more than 27,000 Earth masses. Both objects are made mainly from hydrogen and helium, but one has enough gravity to compress and heat its centre until hydrogen fusion can continue for an extremely long time. Size alone does not determine what an object becomes. The amount of matter matters, but so does the way that matter behaves under pressure. At everyday scales, adding more material usually makes an object larger. A larger pile of books takes up more space than a smaller pile, unless someone has become unusually determined with a hydraulic press. Gas giants, brown dwarfs, and the smallest stars do not follow that simple rule. As more mass is added, gravity becomes stronger. The increased gravity squeezes the object more tightly. The extra material tries to increase the radius, while compression tries to reduce it. Across a wide range of masses, those effects nearly cancel each other. A brown dwarf containing 50 times Jupiter's mass can have a radius close to Jupiter's. A star with more than 80 Jupiter masses can be narrower than Jupiter. The object grows heavier without becoming proportionally wider. This unusual mass-radius relationship is one reason EBLM J0555-57Ab could hide inside a planet survey. Its shadow resembled the shadow of a giant planet because its diameter genuinely belonged in the same range. The difference was contained in its gravitational pull and in the conditions far below its visible surface. Using the measured mass and radius, astronomers estimated an average density close to 190 grams per cubic centimetre. The uncertainty in the radius means that the exact density is not known with the same precision as the mass, but even the central estimate gives a clear picture of an extremely compact object. Water has a density of about 1 gram per cubic centimetre. Earth's average density is about 5.5. Lead is a little over 11, and osmium, one of the densest naturally occurring elements under ordinary conditions, is around 22.5. The average density of this small star is therefore many times greater than that of osmium. That does not mean the star is a solid ball of metallic material. Its matter is hot, ionized, and compressed into plasma. The comparison simply gives us an everyday reference for how much mass occupies each unit of volume. Average density also hides the structure inside. A star is not equally dense from its centre to its outer layers. Pressure increases as we move inward, because each layer must support the material above it. The core is much denser than the average, while the thin outer atmosphere is far less dense. There is no solid surface marking the place where the star begins. What astronomers call the surface is usually the photosphere, the layer from which most of the visible radiation escapes. Beneath it, temperature, density, and pressure rise continuously. If a spacecraft could somehow approach without being destroyed, it would not land on firm ground. It would enter increasingly dense gas and plasma. Long before reaching anything resembling the interior, heat, radiation, pressure, and gravity would have settled the question of whether the visit was sensible. The surface gravity is estimated to be roughly 300 times the gravity at Earth's surface. A person with a mass of 70 kilograms would still have a mass of 70 kilograms there, but their weight would correspond to the force produced by more than 20,000 kilograms under Earth gravity. This comparison is only illustrative, because no person could stand on the photosphere. There would be no platform, no stable footing, and no opportunity to complain that the luggage allowance had become unreasonable. The value can be understood from a simple relationship. Surface gravity increases with mass and decreases with the square of the radius. EBLM J0555-57Ab has much less mass than the Sun, but it is also much smaller. Its material is concentrated close to the centre, so the gravitational acceleration near its outer layers becomes very large. The Sun's surface gravity is about 28 times Earth's. The tiny star's surface gravity is more than 10 times stronger than the Sun's, even though the Sun contains over 12 times more mass. That sounds contradictory until radius is included. The Sun's material is spread through a sphere almost 1.4 million kilometres across. EBL J0555-57Ab concentrates its smaller mass into a body only around 1/10 as wide. Distance from the centre makes a major difference. The same concentration gives the star an escape velocity of roughly 600 kilometers per second. Escape velocity is the speed an object would need near the surface to move away without further propulsion, ignoring complications such as atmospheric resistance in the nearby primary star. That value is close to the escape velocity from the surface of the Sun. The similarity occurs because the ratio of mass to radius is not very different for the two stars. The small star has far less mass, but its radius has also been reduced by a comparable factor. A rocket travelling at 600 kilometers per second would cross the distance from London to New York in roughly 10 seconds, assuming the planet, atmosphere, route, and passengers had all agreed to tolerate the arrangement. Even at that speed, leaving the small star would require overcoming an enormous gravitational well. Gravity is not merely something acting at the surface. It controls the entire structure of the star. Every layer is pulled inward by the mass beneath it. If nothing opposed that pull, the object would continue collapsing. The collapse is resisted by pressure. Deep inside a normal star, hot particles move rapidly and collide. Radiation also contributes pressure, although radiation pressure is far less important in a low-mass star than it is in a very massive one. Together, these effects support the overlying material. A stable star exists in hydrostatic equilibrium. Gravity pulls inward, while pressure pushes outward. The star is not motionless at the microscopic level. Its plasma is active, energy moves through it, and nuclear reactions occur in the centre. On the larger scale, however, the opposing effects remain balanced. The balance adjusts itself. Suppose gravity compresses the core slightly. Compression raises the temperature and pressure. Nuclear reactions can speed up, producing more energy and increasing outward support. The star then expands slightly, cooling the core and slowing the reactions. If the core cools too much, pressure falls, gravity contracts the star, and the temperature rises again. This feedback allows a main sequence star to remain stable over long periods. The process is sometimes compared with a thermostat, although most household thermostats do not operate by squeezing several octillion tons of plasma. The principle is that a change in one direction triggers effects that push the system back toward balance. For EBLM J0555-57Ab, achieving that balance was not guaranteed. Its mass lies close to the lowest value capable of sustaining ordinary hydrogen fusion. During formation, the object began as part of a collapsing cloud of gas and dust. Gravity drew material inward. As the young object contracted, gravitational energy was converted into heat. The centre became denser and hotter. Whether it would become a star depended on whether the core could reach fusion conditions before another form of pressure prevented further heating. To understand that limit, we need to look more closely at what happens when matter is compressed. In ordinary gas, pressure depends strongly on temperature. Heat the particles, and they move faster. Cool them, and pressure decreases. At very high densities, quantum mechanics introduces an additional effect called electron degeneracy pressure. Electrons cannot all occupy the same quantum state. As matter is squeezed, the available low-energy states fill up, and the electrons resist further compression. This pressure does not depend on temperature in the same way as ordinary thermal pressure. Cooling the object does not simply remove it. Electron degeneracy can support dense bodies even when they are not hot enough to sustain ordinary hydrogen fusion. Brown dwarfs are strongly influenced by this effect. A brown dwarf forms through gravitational contraction, and its centre heats for a time. If its mass is too low, electron degeneracy pressure becomes important before the core reaches the conditions needed for stable hydrogen burning. Contraction then slows or stops. The central temperature no longer rises enough to establish a normal main sequence balance. The brown dwarf may briefly fuse deuterium if it is massive enough, and the heaviest examples may also burn lithium, but they cannot sustain the long-term fusion of ordinary hydrogen that defines a true star. Adding mass changes the outcome. Stronger gravity drives the interior to higher pressure and temperature. At around the boundary occupied by EBLM J0555-57Ab, the core can become hot enough for hydrogen fusion, before degeneracy prevents the required conditions from being maintained. The difference between the most massive brown dwarfs and the least massive stars is therefore not a large difference in diameter. It is a difference in what happens at the centre. Two objects can look similar from the outside. Both may be about the size of Jupiter. Both may have cool atmospheres and emit much of their energy in infrared wavelengths. One gradually cools because it has no lasting internal fusion source. The other settles into a stable state and continues converting hydrogen into helium. EBLM J0555-57Ab crossed that boundary by a relatively small margin. Its measured mass places it just above many theoretical estimates of the hydrogen-burning minimum for its composition. It is not barely a star because its fusion switches on and off every few minutes. It is barely a star because a modest reduction in mass during formation could have placed it on the other side of the physical limit. Inside the core, hydrogen fusion proceeds mainly through the proton-proton chain. The same broad process powers the Sun. Hydrogen nuclei, which are individual protons, eventually combine through several reactions to produce helium. The complete sequence releases energy, because the final helium nucleus has slightly less mass than the particles that formed it. The missing mass is converted into energy according to the relationship between mass and energy described by Einstein. The first reaction is extremely slow. Two protons must interact, and one must change into a neutron through the weak nuclear force. The rarity of this reaction is one reason stars can remain stable for billions or trillions of years, rather than consuming all of their fuel in one spectacular afternoon. In a low-mass star, the core temperature is lower than it is in the Sun. The fusion rate is therefore slower. EBLM J0555-57Ab produces far less energy per second than the Sun, but it also needs much less outward pressure to support its lower total mass. The star does not need to shine brightly to remain stable. It only needs to generate enough energy to balance its own gravity. That modest energy output helps explain why very low-mass stars are so faint. Surface temperature and luminosity both decrease toward the bottom of the main sequence. Much of the radiation emerges at red and infrared wavelengths, rather than in the range where human eyes are most sensitive. Seen from Earth beside a hotter primary, the small companion contributes very little visible light. Its gravitational influence is far easier to detect than its own glow. It weighs heavily on the orbit while remaining almost absent from the combined spectrum. The interior is expected to be fully convective. In stars such as the Sun, energy produced in the core first moves through a radiative region. Photons are repeatedly absorbed and re-emitted, taking a very indirect route outward. Closer to the surface, convection becomes dominant. Very low-mass stars behave differently. Convection can carry energy through nearly the entire interior. Hot material rises, cooler material sinks, and the star is mixed from the core toward the surface. This mixing changes how the hydrogen supply is used. The Sun cannot efficiently deliver all of its hydrogen into the central fusion region. Much of its fuel remains outside the core during its main sequence life. A fully convective red dwarf can circulate material through a much larger fraction of its volume. Fresh hydrogen continues to reach the central region, while helium produced by fusion is moved outward. The star can use its fuel more thoroughly. Its low fusion rate and efficient mixing give it an expected lifetime far beyond that of the Sun. The smallest hydrogen-burning stars may remain on the main sequence for trillions of years. The universe is only about 13.8 billion years old, so none of them has completed that full lifespan. Astronomers have never watched such a star reach its predicted final stages because the universe has not provided enough time. This makes EBLM J0555-57Ab an object with an unusual combination of extremes. It is close to the minimum stellar mass, yet it may survive longer than almost every larger star. It has one of the smallest measured stellar radii, yet its surface gravity is much stronger than the Sun's. It produces little visible light, yet its core maintains a nuclear reaction that may continue for trillions of years. Greater mass does not always mean a longer life. In stars, the opposite is usually true. Massive stars contain more fuel, but they burn it at a much faster rate. The largest stars can live for only a few million years before reaching violent final stages. Low-mass stars behave more cautiously. Their cores are cooler, their fusion is slower, and their fuel is used efficiently. They have less material available, but their rate of consumption is so low that their lifetimes become enormous. The small companion's mass also affects the larger star through the orbit. Although Ab contains only about 7% of the primary's mass, that is enough to pull the primary back and forth at several kilometers per second. Had the companion been a planet, the primary's movement would have been much smaller. The strong radial velocity signal was one of the clearest signs that the planet-sized shadow belonged to a stellar mass body. The orbit demonstrates the difference between appearance and gravitational reality. Light showed a small disk. Motion revealed a heavy companion. Neither measurement contradicted the other. They described an object that is genuinely small and genuinely massive. This distinction becomes particularly useful when considering how difficult it would be to identify a similar object without an eclipse. An isolated low-mass star might appear only as a faint red or infrared source. Its luminosity could be compared with theoretical models, but mass and radius would be harder to determine directly. In an eclipsing binary, the companion's weight is written into the primary's motion. The system becomes a set of scales provided by gravity. Orbital period, velocity, inclination, and eclipse shape combine to reveal what cannot be seen in an image. Even then, the word weight can create the wrong picture. The star is not heavy because it contains unusually dense elements. Hydrogen and helium still dominate. It is heavy because there is an enormous quantity of those light elements. Under ordinary conditions, hydrogen is a very low-density gas. Inside a star, ordinary conditions have been politely removed from consideration. Gravity compresses the material, strips electrons from nuclei, and creates pressures that cannot be reproduced on a large scale in any laboratory. The pressure at the core is not supplied by a rigid container. The container is gravity itself. Every part of the star attracts every other part. The outer layers press down because they are being pulled inward, while the deeper material supports them through thermal and quantum pressure. Remove enough mass, and gravity weakens. The core cannot become hot enough for sustained fusion. Add enough mass, and the object crosses the stellar boundary. Continue adding mass, and the radius eventually begins growing more clearly with the total amount of material. EBLM J0555-57Ab sits near the point where the mass-radius relationship turns. Below it are brown dwarfs with similar sizes but no stable hydrogen-burning core. Above it are red dwarfs that gradually become wider and more luminous as mass increases. This turning point is not one perfectly sharp mass applying to every possible object. Chemical composition changes the internal opacity, temperature, pressure, and efficiency of fusion. A star with one mixture of elements may reach stable hydrogen burning at a slightly different mass from one with another mixture. Age can influence radius as well. Young low-mass objects are still contracting and can be larger than older objects of the same mass. Magnetic activity in star spots may also make some low-mass stars appear larger than standard models predict. That problem has become an important area of stellar research. Many measured low-mass stars in close binary systems have radii larger than theoretical calculations expect. Their temperatures may also be cooler. Strong magnetic fields and rapid rotation are leading explanations, although the details remain under study. The radius of EBLM J0555-57Ab was found to be broadly consistent with models for a very low mass, relatively metal-poor star. The measurement uncertainty was large enough that it could not settle every question about low-mass stellar structure, but its position near the bottom of the main sequence made it valuable. A more precise radius would allow a stricter test. Astronomers could compare the observed object with models describing how matter behaves under high pressure, how convection transports energy, and how chemical composition affects the hydrogen burning limit. That is why the star's weight matters beyond the appeal of a record. It gives researchers a real object near a theoretically important boundary. Its mass is not an interesting number on its own. It is the reason the core reached fusion conditions. Its radius is not merely small, It reveals how strongly gravity compressed the matter. The density, surface gravity, and fusion state all follow from the combination. 85 Jupiter masses spread through a sun-sized body would produce one kind of star. The same mass compressed into a Saturn-sized sphere creates the compact object observed in this system. Yet the compression cannot continue without limit. As mass decreases toward the bottom of the main sequence, ordinary expectations about hotter cores and smaller radii begin to compete with quantum pressure. Eventually, an object can no longer raise its central temperature enough to become a lasting hydrogen-burning star. EBLM J0555-57Ab stands close to that transition. The narrow physical boundary is maintained by a reaction taking place deep inside EBLM J0555-57Ab. The reaction is not violent in the way an explosion is violent. It does not consume the star all at once, and it does not make the object flare with the brilliance of a massive blue star. Hydrogen is converted into helium at a very slow rate, producing just enough energy to support the star against gravity. Calling it a gentle fire is useful as long as we remember that ordinary fire is not involved. A candle burns through a chemical reaction. Its atoms rearrange their electrons, releasing energy stored in molecular bonds. A star works through nuclear fusion. The nuclei of atoms are changed, and a small amount of mass becomes energy. The difference is considerable. Chemical reactions affect the outer electronic structure of atoms. Nuclear reactions reach into the nucleus itself. Each successful fusion sequence releases far more energy than any chemical reaction involving the same amount of material. None of this would have started without gravitational contraction. EBLM J0555-57Ab began as gas within a collapsing region of a larger cloud. As gravity pulled the material inward, the object became denser. Particles fell toward the center, collided, and converted gravitational energy into heat. A young star does not begin with hydrogen fusion already running. It first shines partly because it is contracting. The inward movement raises the pressure and temperature of the core. If the object contains enough mass, the central conditions eventually become suitable for sustained fusion. For a body near the minimum stellar mass, reaching that point is difficult. Gravity must compress the core strongly enough to overcome the effects that resist further contraction. EBLM J0555-57Ab succeeded because its mass, around 0.081 solar masses, or roughly 85 Jupiter masses, lies just above the expected hydrogen-burning minimum for an object with its measured composition. Models show that this minimum is not one universal number. It changes with metallicity and with the physical treatment of dense hydrogen and helium. Hydrogen nuclei are protons, and protons carry positive electrical charge. Two positive charges repel each other. Before two protons can participate in fusion, they must approach closely enough for the strong nuclear force to take over. The strong nuclear force acts over extremely short distances. At larger separations, electrical repulsion dominates. This creates an energy barrier between the protons, often called the Coulomb barrier. A first explanation might suggest that the core simply becomes hot enough for protons to smash through that barrier. Temperature does help because hotter particles move more quickly. Even in the center of a star, however, most protons do not have enough energy to cross the barrier in the classical sense. Quantum mechanics provides the remaining part of the explanation. Particles do not behave only like tiny solid balls following perfectly definite paths. They are described by quantum wave functions, which allow a small probability that a proton can pass through a barrier it could not classically climb over. This is called quantum tunneling. The proton does not drill a tunnel, or briefly borrow a miniature shovel. Its quantum description allows a non-zero probability of appearing on the other side of the energy barrier. Most close encounters between protons do not result in fusion. The probability is extremely low. A star compensates by containing an enormous number of protons and allowing them to collide repeatedly over very long periods. Even when two protons approach closely enough, another unlikely step must occur. The simplest stable nucleus containing two protons does not exist. One of the protons must change into a neutron so that the pair can form deuterium, a heavy form of hydrogen containing one proton and one neutron. That conversion is controlled by the weak nuclear interaction. During the reaction, a positron and an electron neutrino are also produced. The positron soon meets an electron, and the two annihilate, adding more energy to the surrounding plasma. The weak interaction makes this first step exceptionally slow. That slowness is fortunate. If the first reaction in the proton-proton chain occurred easily, stars would burn through their hydrogen much faster. The Sun would not have remained stable for billions of years, and a tiny star near the hydrogen burning limit would have a very different life. Once deuterium has formed, it can combine with another proton to produce helium-3. Two helium-3 nuclei can later combine to make helium-4, releasing two protons back into the plasma. The full process begins with 4 hydrogen nuclei and ends with one helium-4 nucleus, along with positrons, neutrinos, and energy. The helium nucleus has slightly less mass than the original particles taken together. That difference in mass has been converted into energy. A large portion of the released energy remains in the star as kinetic energy and radiation. Neutrinos interact very weakly with matter, so they can escape from the core much more directly. They carry away a fraction of the energy without waiting for the rest of the star to make room. The photons produced in the interior do not travel straight to the surface. They are absorbed, scattered, and re-emitted many times. In a star as small as EBLM J0555-57Ab, however, energy transport is expected to be dominated by convection through most or all of the interior rather than by a large stable radiative zone. Very low-mass main-sequence stars below roughly 0.35 solar masses are generally expected to be fully convective. Their material circulates throughout nearly the whole body, carrying energy outward and mixing the chemical contents. EBLM observations of other very low-mass eclipsing stars have been used to test models in this fully convective regime. Convection can be pictured as a continuous movement of plasma. Hotter material rises because it is less dense than its surroundings. As it moves outward, it releases energy and cools. Denser material sinks, returning hydrogen-rich plasma toward the center. The movement is not a single neat loop. The interior contains many changing flows, cells, and turbulent motions. There is no tiny conveyor belt marked fresh hydrogen this way, though the overall effect is similar. This mixing gives the smallest stars an advantage in fuel use. A star like the Sun fuses hydrogen mainly in its central region, while a large amount of hydrogen remains outside the core. The Sun will eventually leave the main sequence even though much of its total hydrogen has never entered the central fusion zone. A fully convective star can draw on hydrogen from a much larger fraction of its interior. Helium produced in the center is circulated outward, while hydrogen is brought inward. The available fuel is used more thoroughly. Efficiency alone does not explain the enormous lifetime. The fusion rate is also very low. The core of a minimum mass star is cooler than the core of the Sun. Nuclear reactions are highly sensitive to temperature, so even a modest reduction in central temperature produces a much slower rate of energy generation. EBLM J0555-57Ab does not need to match the Sun's output. Its total mass is much smaller, so less pressure is required to prevent collapse. It can maintain equilibrium while producing only a small fraction of the Sun's luminosity. A useful comparison is a building supported by heating air inside it. Assuming the building has been designed by someone who should not be responsible for buildings. A very large structure would need a great deal of pressure. A smaller one would require much less. EBLM J0555-57Ab can remain stable with a modest nuclear output because there is less total material pulling inward. Its low luminosity does not mean that fusion is unreliable. Once a genuine low-mass star settles onto the main sequence, it can maintain stable hydrogen burning, The reaction rate adjusts with the internal conditions. If the fusion rate decreases, the star loses a little outward support. Gravity contracts the interior, raising the core temperature and density. The increased temperature makes fusion more likely, restoring the energy output. If the fusion rate becomes too high, additional energy causes the star to expand slightly. Expansion cools the core, which slows the nuclear reactions. This negative feedback helps regulate the star. The balance does not require conscious management, which is helpful because the position of Stellar Thermostat Inspector has remained vacant for some time. It follows automatically from the relationship between gravity, temperature, pressure, and the temperature sensitivity of fusion. For a star close to the hydrogen burning limit, the equilibrium lies near the weakest sustainable end of the main sequence. The core is hot enough for the proton-proton chain to provide lasting support, but not by an enormous margin. A brown dwarf follows a similar early path. It forms through gravitational collapse, contracts, and heats. The centre may reach millions of degrees and some nuclear reactions can occur. The key difference is whether ordinary hydrogen fusion becomes a stable, long-term source of enough energy to halt continued contraction. Objects above about 13 Jupiter masses can burn deuterium for a period, although the precise deuterium burning boundary depends on composition and on how the criterion is defined. Deuterium is easier to fuse than ordinary hydrogen because its reaction does not require the same slow, initial proton-to-neutron conversion. It is also rare, so the available supply is consumed relatively quickly. Burning deuterium does not make an object a normal main sequence star. Many brown dwarfs briefly perform that reaction during their youth, then return to gradual cooling after their deuterium has been depleted. The lasting distinction involves the fusion of ordinary hydrogen. A true star establishes an equilibrium in which hydrogen burning supplies the energy needed to support it. A brown dwarf cannot maintain that state. As a brown dwarf contracts, its density rises. Electrons are squeezed into increasingly limited quantum states, and electron degeneracy pressure becomes important. This pressure resists compression for reasons connected to the Pauli exclusion principle, which prevents identical fermions from occupying the same quantum state. Unlike ordinary gas pressure, degeneracy pressure does not depend mainly on heat. Cooling the object does not remove it. Once degeneracy becomes strong enough, additional contraction fails to raise the core temperature in the simple way required for hydrogen ignition. The brown dwarf reaches a point where its central temperature stops increasing effectively. It is supported partly by degeneracy pressure, but it lacks a permanent fusion source. It radiates away stored thermal energy and gradually becomes cooler and fainter. A minimum mass star arrives at a different outcome. Its gravity is strong enough to bring the core into the hydrogen burning regime before degeneracy prevents the needed temperature increase. Fusion begins contributing enough energy to halt the contraction and maintain a stable stellar structure. The line is narrow because the competing processes change rapidly with mass. Adding a few Jupiter masses near the limit can decide whether the object becomes a long-lived star or a cooling brown dwarf. That does not mean every object above one exact mass must be a star, and every object below it must be a brown dwarf in all circumstances. Chemical composition affects opacity and internal structure. Helium abundance changes the mean molecular weight. Metallicity influences the atmosphere and the way radiation escapes. Modern calculations of dense hydrogen-helium mixtures can also shift the predicted threshold. Older low-mass models found hydrogen-burning minimum masses varying with metallicity, generally increasing as metal abundance decreases. Updated work using a newer hydrogen-helium equation of state placed the solar metallicity minimum near 0.075 solar masses, or about 78.5 Jupiter masses, under the particular atmosphere models used. These values illustrate why the limit is better treated as a narrow region than as a universal number printed on a gate. EBLM J0555-57A was measured to have an iron abundance below the Sun's. The tiny companion presumably formed from the same material, so its lower metallicity is relevant when comparing it with models. At about 0.081 solar masses, EBLM J0555-57Ab lies above the hydrogen burning limit expected for its composition. Its measured radius was also consistent with low-mass stellar models within the observational uncertainty. The discovery therefore did not identify an object with an impossible combination of mass and size. It provided a rare measured example near the point where the models predict that stars should begin. The energy output of such a star would emerge mainly at red and infrared wavelengths. A cooler stellar surface produces a spectrum shifted toward longer wavelengths compared with the Sun. That description should not be confused with a cold surface. Even the coolest hydrogen-burning stars have temperatures of thousands of Kelvin. They are cool only by stellar standards, a phrase that has allowed astronomy to describe several objects capable of vaporizing spacecraft as relatively chilly. Beside the hotter and larger primary, the companion's light is overwhelmed. EBLM J0555-57Ab contributes too little visible light for its spectral lines to stand out clearly in the observations used for the discovery. Its fusion is therefore known mainly through classification and modelling, rather than through a direct measurement of nuclear reactions inside this particular star. Astronomers measure the mass, radius, composition of the system, orbit, and luminosity where possible. They then compare those properties with physical models that calculate whether an object of that mass and composition sustains hydrogen burning. No instrument can be lowered into the core to check whether the proton-proton chain is following the instructions. Stellar interiors are inferred through tested physical laws and through observations of many objects at different masses, ages, and compositions. The same approach is used for the Sun, although solar neutrinos and helioseismology provide additional direct tests of its interior. For a faint companion hundreds of light-years away, the evidence is less detailed but still strong enough to place it on the stellar side of the boundary. Its mass is especially important. Even at the lower end of the reported uncertainty, the companion remains close to the expected stellar threshold. The central estimate places it above updated solar metallicity limits and near the higher thresholds predicted for lower metallicities. The radius supports the interpretation because it agrees with calculations of compact, old, very low-mass stars. A young brown dwarf or giant planet can have a similar or larger radius, but mass and evolutionary behavior separate the possibilities. Hydrogen fusion also changes the object's long-term future. A brown dwarf fades continuously after its early heat, and limited nuclear fuel are lost. A low-mass star settles into a prolonged main sequence period, during which the energy from hydrogen fusion replaces the energy radiated from the surface. The smallest red dwarfs are expected to remain active for trillions of years. Exact lifetimes depend on mass, composition, and the stellar models used, but all reasonable estimates extend far beyond the Sun's roughly 10 billion year main sequence lifetime. EBLM J0555-57. AB may have been shining for a few billion years, yet it has consumed only a small fraction of its usable hydrogen. The universe itself is not old enough for any minimum mass star to have completed the full evolution predicted for it. Consequently, astronomers cannot point to a nearby ancient example and show what such a star looks like after several trillion years. The late stages exist in computer calculations rather than in current observations. Models predict that fully convective low-mass stars will gradually change as helium accumulates. Because mixing distributes helium throughout the interior, they do not develop exactly the same sharply separated core structure as the Sun. Over immense timescales, they are expected to become hotter and more luminous rather than expanding into ordinary red giants in the same way as solar mass stars. Eventually, after exhausting hydrogen, they may end as helium-rich white dwarfs without passing through the familiar giant star stages. That future lies so far ahead that many other cosmic changes will occur first. Current star formation will decline, existing massive stars will be long gone, and galaxies will continue to evolve. the smallest stars could remain among the last conventional sources of starlight. For EBLM J0555-57Ab, the nearby primary complicates the distant future. The larger star will evolve much sooner. As it exhausts central hydrogen, it will eventually expand, and the close binary interaction could alter both objects. The small companion orbits at only a fraction of the Earth-Sun distance. A future expansion of the primary may lead to tidal changes, mass transfer, or even engulfment, depending on the detailed evolution of the system. The tiny star's theoretical individual lifetime may therefore be far longer than the time it remains in its present arrangement. Those events are not imminent. The system has plenty of ordinary stellar evolution ahead of it, and the exact outcome requires modelling beyond the measurements used to establish the companion's current properties. For now, the reaction in the little star continues. Protons collide, almost all of them separate again. On rare occasions, quantum tunneling brings them close enough. The weak interaction converts one proton into a neutron, and the proton-proton chain moves forward. Each individual sequence releases a very small amount of energy. The number of reactions across the core is large enough to support the whole star. The total output remains faint compared with the Sun, but it is sufficient. This is the main achievement of EBLM J0555-57Ab. It does not merely produce some nuclear reactions. A young planet or brown dwarf may experience limited fusion under certain conditions. The small star maintains ordinary hydrogen burning as the lasting source of its internal support. That distinction may sound clear while we focus on one measured object, yet the broader boundary is less tidy. Brown dwarfs can share the same radius, similar temperatures, similar colours, and even some early fusion reactions. The least massive stars can be extremely faint and difficult to separate from the heaviest brown dwarfs by appearance alone. The comparison becomes easier once we separate three questions that are often mixed together. How did the object form? What reactions have occurred inside it? And what supplies the energy leaving its surface today? For the boundary between a brown dwarf and a true star, the third question is the most important. A star sustains ordinary hydrogen fusion as its main long-term energy source. A brown dwarf does not. It may have fused deuterium when it was young, and a sufficiently massive brown dwarf may destroy lithium, but neither process provides the stable, continuing support created by ordinary hydrogen burning. This distinction is less obvious than it sounds because stars and brown dwarfs overlap in several visible properties. The most massive brown dwarfs can be about the same width as the smallest stars. They can have similar surface temperatures at certain ages. Their atmospheres can contain some of the same atoms and molecules, and both may appear as faint red or infrared points of light. A photograph would not necessarily settle the question. Even a spectrum can be difficult to interpret without knowing the object's age, distance, mass, and chemical composition. A young brown dwarf can be hotter and brighter than an old, very low-mass star. Given enough time, the brown dwarf cools, while the star remains supported by fusion. Mass provides a strong clue, although the dividing value is not exactly the same for every object. Updated models of dense hydrogen and helium place the minimum mass for sustained hydrogen burning near 0.075 solar masses, or about 78.5 Jupiter masses for solar composition under the particular atmospheric models used. Changes in metallicity and helium abundance can move that boundary. EBLM J0555-57Ab at roughly 0.081 solar masses sits only a short distance above it. That difference of a few Jupiter masses may not sound large beside a star, but near the limit it changes the entire future of the object. One body becomes a stable member of the main sequence. Another begins a long process of cooling and fading. Both may start in a similar way. A dense region inside a cloud of gas collapses under gravity. Material falls inward, the forming object becomes hotter, and a disk may develop around it. matter can continue arriving from the surrounding cloud or disk until that supply is reduced or cut off. Brown dwarfs are not simply large planets that failed an exam. Observations of young objects show that they can form through cloud collapse and display disks, accretion, and outflows resembling those found around young stars. The formation processes overlap, especially at low masses, so it is not always useful to imagine a clean assembly line with planets on one side and stars on the other. A planet such as Jupiter is generally thought to form inside a disk around a star, either by building a solid core and collecting gas, or through instability in the disk. Brown dwarfs can form more directly from collapsing gas, though nature does not always respect a simple textbook division. The boundary between planets and brown dwarfs is therefore debated in a different way from the boundary between brown dwarfs and stars. A commonly used value of 13 Jupiter masses refers to the approximate onset of deuterium burning, but deuterium burning is temporary and depends on composition. It does not tell us with certainty how an object formed. At the upper end of the brown dwarf range, the lasting question is simpler. Can the object sustain fusion of ordinary hydrogen strongly enough to replace the energy escaping from its surface? For EBLM J0555-57Ab, the answer is yes. Its core reached the necessary conditions, and the star settled into hydrostatic equilibrium. Gravity pulls inward, while pressure supported by heat and nuclear energy acts outward. It is not shrinking and cooling in the way a brown dwarf of similar age would. Consider an object just below the limit. During its early contraction, the centre becomes hotter. Some fusion reactions may begin, but ordinary hydrogen burning never becomes strong enough to supply the surface luminosity over the long term. Electron degeneracy pressure gradually becomes important. Continued compression no longer raises the central temperature efficiently. The object stops contracting before it can establish a stable hydrogen-burning state. It then radiates away the heat left from formation. Its luminosity falls, its surface temperature decreases. The interior remains supported partly by degeneracy pressure rather than by the thermal pressure maintained through sustained fusion. A brown dwarf does not suddenly go dark. Cooling takes a very long time, and the object continues emitting infrared radiation. Young brown dwarfs can be warm and relatively bright because they retain considerable heat from their formation. Age changes their appearance substantially. A brown dwarf with a given mass may begin with a temperature similar to that of a very small star. Hundreds of millions or billions of years later, it can be much cooler. This creates a problem for astronomers. Temperature alone cannot provide a unique mass. A cool object might be a young, low-mass brown dwarf, an older, more massive brown dwarf, or a star very close to the hydrogen-burning boundary. Luminosity has the same difficulty. Brown dwarfs do not settle onto a permanent main-sequence relationship between mass and brightness. They move through a sequence of temperatures and luminosities as they cool. Estimating their mass from light therefore requires an age, while estimating their age often requires a mass. Astronomy has several arrangements like this, usually waiting until everyone has become comfortable before introducing the circular dependency. Evolution models help by calculating how objects of different masses should contract, cool, and change their atmospheres over time. These models include the behavior of hydrogen and helium at high density, convection inside the object, radiation through the atmosphere, and the formation of molecules and clouds. At cooler temperatures, the atmosphere can contain molecules that would not survive in an ordinary star like the Sun. Metal compounds and silicate particles can form clouds. As temperatures fall farther, methane becomes prominent, followed at still lower temperatures by water, ammonia, and other molecules. This progression helped astronomers create the LT and Y spectral classes used for many brown dwarfs. The letters continue beyond the traditional O, B, A, F, G, K, and M stellar sequence, because brown dwarf atmospheres reach conditions not represented well by the older system. The classification does not map directly onto mass. A young object and an old object of different masses can share the same spectral type. It describes the observed atmosphere, not a single fixed place on a mass scale. The least massive stars are usually late M-type objects while they remain on the main sequence. Their atmospheres are cool enough for molecules such as titanium oxide and water vapour to affect their spectra, but their internal fusion prevents the continuing decline in luminosity experienced by brown dwarfs. EBLM J0555-57. AB has not been given the same detailed isolated spectral classification that a nearby single red dwarf might receive. Its own light is hidden beside the brighter primary. Its identity comes mainly from its measured mass, radius, orbit, and agreement with models. In another system, astronomers might search for lithium to help distinguish a low-mass star from a brown dwarf. Lithium is destroyed at a lower central temperature than ordinary hydrogen requires. Objects above a certain mass eventually become hot enough to burn their original lithium, while lower mass brown dwarfs preserve it. Finding lithium in an old, cool object can therefore indicate that the core never became hot enough to destroy it. This is called the lithium test. The exact mass boundary depends on age and model assumptions, and observations show that the transition requires careful calibration rather than one universal number. The test is most useful when the object spectrum can be observed clearly. That is difficult for EBLM J0555-57Ab because the hotter primary dominates the system's visible light. A clean lithium measurement from the small companion would require separating a very faint spectrum from a much brighter one. Its dynamical mass already gives stronger evidence. At about 85 Jupiter masses, it lies above most predictions for the hydrogen burning minimum at its metallicity. The measured radius also fits the compact size expected for a true, old, very low mass star. The smallest stars and the heaviest brown dwarfs can still exchange places in a simple temperature ranking. A young brown dwarf may be warmer than an old red dwarf. The difference appears over time. The brown dwarf keeps cooling because it has no permanent nuclear source capable of balancing its energy loss. The red dwarf reaches a regulated state. Its surface radiates energy, fusion replaces that energy, and gravity adjusts the core conditions when the balance shifts. For a star as small as EBLM J0555-57Ab, this regulated output is extremely low compared with the Sun. That is precisely why the fuel lasts so long. The Sun contains more hydrogen, but it consumes that hydrogen at a much higher rate. Its core temperature is greater, nuclear reactions occur more frequently, and its luminosity is vastly larger. Low-mass stars follow the opposite strategy without intending to. Their cores operate at lower temperatures. The proton-proton chain proceeds slowly. Their surfaces are cool, and their energy output is modest. They also use their fuel more thoroughly. EBLM J0555-57. AB is expected to be fully convective. Material moves throughout most or all of the interior rather than leaving a stable radiative region around the core. Hydrogen from outer regions can circulate inward. Helium produced near the centre can be carried outward. The star does not quickly build a separate helium core while leaving most of its hydrogen beyond reach. The Sun will leave the main sequence when hydrogen becomes depleted in its core, even though a large amount of hydrogen remains elsewhere inside it. A fully convective red dwarf can continue mixing its supply and make use of a much greater fraction of the available fuel. Slow consumption and efficient mixing produce an enormous theoretical lifespan. Models of the long-term future of low-mass stars suggest that an isolated object near 0.08 solar masses may continue burning hydrogen for roughly 10 trillion years or more, depending on its exact mass and composition. The current age of the universe is only a small fraction of that duration. No astronomer has observed a minimum mass red dwarf reach old age in the usual sense. Even the earliest low-mass stars formed after the beginning of the universe have completed only a tiny part of their expected main sequence lives. Everything about their final development must therefore be calculated. Models can be tested against stars at younger ages, but the last stages cannot yet be compared with a real example. For most stars, astronomers can observe different objects representing different phases. We see young stars forming, main sequence stars burning hydrogen, red giants expanding, and white dwarfs cooling. No one has to wait for one sun-like star to complete its entire life. The oldest red dwarfs have not had enough time to approach the predicted later phases. The universe does not contain an ancient population several trillion years old for comparison. The model is being asked to extend far beyond the current observational record. During most of that time, a tiny red star changes very slowly. It continues converting hydrogen into helium while remaining compact. Its luminosity gradually increases as its internal composition changes, but the process is far less dramatic than the later evolution of a massive star. Helium has a different effect on the stellar structure from hydrogen. As the proportion of helium rises throughout a fully convective star, the average mass of the particles changes, the core adjusts, and fusion gradually proceeds under different conditions. The star is expected to become hotter and more luminous over immense timescales. Because it remains mixed, it does not develop the same compact helium core and broad hydrogen-burning shell that cause a sun-like star to expand into a red giant. Some theoretical calculations predict a stage informally called a blue dwarf. The name does not describe a new class that astronomers have observed through telescopes. It describes a predicted future state in which a very low-mass star becomes hotter and bluer while remaining relatively compact. The term can create the impression that the star suddenly changes colour one afternoon. The transition would take longer than the entire present age of the universe many times over. No one would be checking the difference between Monday and Tuesday. As hydrogen becomes severely depleted, the star's luminosity can increase more noticeably. Eventually, nuclear burning can no longer maintain the previous equilibrium. A very low-mass star is not expected to ignite helium. Its core never reaches the temperature required for the triple alpha process that converts helium into carbon. That reaction needs far more extreme conditions than hydrogen fusion. After exhausting usable hydrogen, the object is expected to contract into a helium-white dwarf. It would then cool gradually, no longer supported by active fusion. In ordinary current-day stellar evolution, helium-white dwarfs are usually associated with binary systems. A star can lose its outer layers to a companion before its helium core grows massive enough to ignite. The universe is too young for an isolated minimum mass red dwarf to create a helium-white dwarf through its full natural lifespan. Far in the future, that could change. Low-mass stars may become helium-white dwarfs without requiring a companion, simply because they never become hot enough to fuse helium. EBLM J0555-57. AB already has a companion, and that makes its actual future less simple than the isolated models. The primary star is more massive and will evolve much sooner. As EBLM J0555-57, A uses its central hydrogen, it will eventually leave the main sequence and expand. The close companion currently orbits at only about 0.082 astronomical units. An expanding primary could interact strongly with it. Tidal forces may change the orbit. Material from the primary could transfer onto the smaller star. The companion might enter the primary's outer envelope, and the two objects could experience a common envelope phase. The final result depends on how large the primary becomes, how much mass it loses, how the orbit changes, and how efficiently orbital energy removes the envelope. These details cannot be read directly from the present observations. Consequently, saying that EBLM J0555-57Ab can burn for trillions of years describes what a star of its mass is physically capable of doing. It does not guarantee that this particular object will remain undisturbed in its current orbit for that entire period. Its larger companion may alter the story much earlier. A star with a theoretical fuel supply for trillions of years can still have its life changed by a neighbour whose own clock runs faster. This is another reason binary systems are useful and complicated. They allow accurate measurements of mass and radius, but they can also modify the evolution of the objects being measured. Close companions may rotate rapidly because of tidal effects. Strong rotation can contribute to magnetic activity. Magnetic fields and star spots can influence measured temperatures and radii. Many low-mass stars in eclipsing binaries have been found to be larger and cooler than some standard models predict. Magnetic activity is one leading explanation. A strong field can alter convection, while dark star spots reduce the average surface temperature and affect the inferred radius. The discovery measurement for EBLM J0555-57Ab was consistent with models within its uncertainty, but that uncertainty was broad enough to leave room for improvement. More precise observations could help determine whether the star is inflated relative to theory or closely follows the predicted radius. Understanding that detail matters near the hydrogen burning limit. The radius depends on the equation of state, chemical composition, age, magnetic activity, and treatment of the atmosphere. A small error in radius produces a large error in density because volume depends on the radius cubed. Better measurements would refine the interior pressure and structure inferred for the star. The atmospheric behavior near the boundary is also difficult to model. Molecules absorb radiation across huge numbers of wavelengths. Dust grains may form under some conditions. Convection must be connected with an atmosphere where radiation finally escapes into space. A model can use the correct mass and still predict the wrong temperature or radius if the atmosphere is treated too simply. This is why measured eclipsing systems remain valuable even when the basic distinction between star and brown dwarf seems settled. Brown dwarfs provide tests on the other side of the line. Their cooling rates depend on the same dense matter physics, atmospheric opacity, convection, and chemical composition. A model that describes the smallest stars should connect smoothly to models of the heaviest brown dwarfs. The newest equations of state improve the treatment of interactions in dense hydrogen-helium mixtures. Those updates change predicted cooling rates, temperatures, luminosities, radii, and the calculated hydrogen burning minimum. The boundary remains an active modelling problem because small changes in the internal physics matter greatly in this narrow mass range. Nature does not produce a wide empty gap between the heaviest brown dwarf and the lightest star. Objects can exist on both sides with very similar masses, radii, and temperatures. The decisive difference appears in their energy budgets. A brown dwarf's luminosity comes mainly from stored heat and continued contraction. A star's luminosity is replenished by sustained hydrogen fusion. That difference becomes more obvious as the objects age. After several billion years, the brown dwarf is cooler and fainter than it was when young. The red dwarf continues operating near a stable main sequence state. After hundreds of billions or trillions of years, the contrast becomes much larger. The brown dwarf has cooled far beyond ordinary stellar temperatures. The star is still fusing hydrogen and may only then be approaching the later stages of its main sequence evolution. EBLM J0555-57Ab is therefore small in width but not temporary. It has crossed the threshold that gives it access to one of the longest possible lives of any conventional star. Its mass is only slightly above the minimum, yet that is enough to maintain the proton-proton chain. Its fully convective interior can circulate fuel. Its low luminosity prevents rapid consumption. Its strong gravity keeps the core under the required pressure. Had it formed with several fewer Jupiter masses, the same object might have spent its existence cooling through the brown dwarf sequence. Instead, it continues replacing the energy lost from its surface. The distinction is not visible in the small silhouette that crossed the primary star. The eclipse showed only that the companion was narrow. The primary's wobble revealed enough mass to place it on the stellar side of the limit. That combination allows the system to do more than establish a size record. It gives astronomers a measured point close to where sustained stars begin, where brown dwarfs continue cooling, and where the behavior of dense hydrogen changes the outcome of formation. Following that point into the future also changes the usual picture of stellar life. The brightest stars are not the longest lasting ones, and the smallest star is not necessarily the least successful. A low output can preserve fuel, complete convection can make more of that fuel available, and a barely sufficient core temperature can support an object for trillions of years. Those properties make the lowest mass stars useful for testing far more than the meaning of the word star. Their radii test dense matter physics, their temperatures test atmospheric models, their binary orbits test gravitational measurements, their long lives affect the future population of galaxies, and their small size changes the kinds of planets that can be detected around them. That broader importance begins with a practical problem. If astronomers cannot describe the smallest stars accurately, they also struggle to describe anything orbiting them accurately. A planet is usually measured relative to its star. During a transit, researchers determine the planet's radius by comparing the amount of starlight blocked with the size of the stellar disk. If the star turns out to be 10% larger than expected, the calculated planet becomes larger as well. Its density changes, its likely composition may change, and conclusions about whether it is rocky, watery, or surrounded by a thick atmosphere can change with it. The star is therefore not merely the bright object in the background, it is part of the measuring equipment. This makes systems like EBLM J0555-57 especially useful. Its eclipsing geometry allows astronomers to measure properties of an extremely low-mass star using orbital mechanics, rather than relying entirely on theoretical predictions. The companion moves in front of the primary, providing information about radius. Its gravity moves the primary, providing information about mass. When those measurements are combined, researchers obtain a real test point near the bottom of the main sequence. That test is valuable because modelling very low-mass stars is surprisingly difficult. A star like the Sun contains plasma under conditions that are already far removed from anything encountered in daily life. But the smallest stars add another complication. Their interiors are cooler and denser. Molecules can form in their atmospheres. Convection dominates a much larger fraction of the interior, and dense hydrogen and helium behave in ways that require careful equations of state. An equation of state tells physicists how matter responds when temperature, density, and pressure change. For an ordinary gas in a classroom experiment, relatively simple relationships can work well. Inside a star, particles are ionized, electrons interact with nuclei, quantum effects become important, and the pressure can reach values that make the air inside a bicycle tyre seem rather undercommitted. If the equation of state is slightly wrong, the predicted radius may be slightly wrong. If the treatment of convection is incomplete, the predicted surface temperature may shift. If the atmosphere absorbs radiation differently from the model, the calculated luminosity changes. These errors become especially important near the hydrogen burning limit because the difference between one class of object and another is already small. EBLM J0555-57. AB provides a particularly useful measurement because it lies close to that limit. Its mass is around 85 Jupiter masses, and its measured radius is comparable to Saturn's. A successful stellar model should be able to reproduce an object with approximately those properties at the appropriate age and chemical composition. If the model predicts that a star of that mass should be much larger, something is missing. If it predicts that the object should not sustain hydrogen fusion at all, something more serious is missing. Astronomers have found that some low-mass stars in eclipsing binaries appear larger than standard models predict. The difference is not always enormous, but it can be several percent, which is a snuff to matter when trying to determine the properties of an orbiting planet. Magnetic activity is one possible explanation. Strong magnetic fields may alter convection inside a star. Star spots can cover significant portions of the surface, changing the average temperature and affecting the radius needed for the star to release its internal energy. Rapid rotation may strengthen magnetic activity. Close binary stars can rotate quickly because tidal interactions connect their rotation with their orbital motion. This means eclipsing binaries provide excellent measurements, while also creating physical conditions that can make them somewhat different from isolated stars. Astronomy does enjoy providing a convenient ruler and then quietly mentioning that the ruler may have a magnetic field. Large samples help solve that problem. If astronomers measure many low-mass stars with different orbital periods, metallicities, rotation rates, and activity levels, they can compare them. Patterns begin to reveal which physical effects matter most. The EBLM project has contributed to that effort by turning objects originally encountered in planet surveys into laboratories for low-mass stellar physics. A signal that fails to become an exoplanet can still become an accurate mass and radius measurement. Those measurements feed directly back into exoplanet science. Small stars are among the most useful places to search for small planets. The reason begins with simple geometry. Imagine Earth crossing the Sun. Earth is tiny compared with the solar disk. During a transit, it blocks only about 0.08% of the Sun's light. Detecting such a shallow change requires very precise observations. Now place the same Earth-sized planet in front of a star only 1/10 the Sun's radius. The planet covers a much larger fraction of the stellar surface. Instead of disappearing against a huge disk, it becomes a relatively substantial silhouette. The transit can become roughly 100 times deeper than an Earth transit across the Sun, depending on the exact stellar radius. Nothing about the planet has changed. The background target has simply become smaller. This is one reason terrestrial planets are easier to discover around red dwarfs. The same advantage appears when astronomers try to examine an atmosphere. During a transit, a tiny amount of starlight passes through the edge of a planet's atmosphere before reaching a telescope. Molecules in that atmosphere absorb particular wavelengths, leaving subtle patterns in the spectrum. For an Earth-sized planet crossing a Sun-sized star, the atmospheric signal is extremely small. Place that planet in front of a much smaller star, and the atmosphere blocks a larger fraction of the available starlight. The measurement remains difficult. It simply moves from extremely discouraging to merely extremely difficult, which in astronomy can count as excellent news. Small stars offer another advantage. They are less massive, so an orbiting planet can move them more noticeably. Just as EBLM J0555-57Ab pulls its primary back and forth, a planet pulls on its host star. The effect is smaller because a planet has far less mass, but high-precision spectrographs can detect the resulting radial velocity changes. For the same planet, a lower mass star responds more strongly than a higher mass star. This makes it easier to estimate the planet's mass. Combine mass from radial velocity with radius from a transit, and density can be calculated. Density then begins to tell us what the planet may be made of. A dense planet may be dominated by rock and metal. A lower density planet could contain large amounts of water, hydrogen, helium, or other volatile material. Two planets with the same radius can have very different interiors, so measuring both mass and radius is essential. Tiny stars therefore give astronomers a useful combination. Their small disks produce deeper planetary transits, and their low masses produce larger gravitational wobbles. There is also the matter of temperature. A low-mass red dwarf emits much less energy than the Sun. A planet does not need to orbit nearly as far away to receive an Earth-like amount of stellar energy. The region where surface temperatures might permit liquid water under suitable atmospheric conditions is called the habitable zone. Around a faint red dwarf, that zone lies close to the star. A close orbit has a short period. Instead of waiting 1 year for another transit, astronomers might wait several days or weeks. Repeated transits accumulate quickly. A telescope can collect many events during a reasonable observing campaign. Each one adds information and improves the combined signal. This advantage is beautifully demonstrated by TRAPPIST-1, another ultra-cool red dwarf, although it is larger than EBLM J0555-57Ab. 7 Earth-sized rocky planets are known to orbit TRAPPIST-1, packed into a region so compact that all 7 would fit comfortably inside the orbit of Mercury if the system were placed around our Sun. Several receive levels of stellar energy that make them important targets in discussions of possible habitability. The discovery of systems like TRAPPIST-1 changed what astronomers could realistically study. Earth-sized planets were no longer objects expected only around Sun-like stars on year-long orbits. Small stars could host compact systems where multiple terrestrial planets produced frequent measurable transits. That does not mean every tiny star should have 7 convenient Earth-sized planets arranged for our telescopes. EBLM J0555-57Ab itself is a poor example of a quiet, isolated red dwarf. It has a much larger stellar companion only about 0.082 astronomical units away. Its environment is dominated by that close binary relationship. We should not quietly invent a family of planets around it simply because planets would make the story more crowded. Its importance to planetary astronomy comes mainly from what it teaches us about stars of similar size and mass. Other isolated red dwarfs can provide very different environments. Many are common, long-lived, and small enough to make terrestrial planets easier to detect. This has made them major targets in the search for nearby rocky worlds. Yet a smaller star does not automatically provide a better home for life. The close habitable zone introduces complications. A planet orbiting near a red dwarf experiences strong tidal forces. Over time, its rotation may become synchronized with its orbit, leaving the same side facing the star. This is often described as tidal locking. The first mental image is not encouraging. One hemisphere appears trapped in permanent daylight while the other remains in endless night. It is easy to imagine the atmosphere boiling on one side and freezing on the other. Climate models show that the outcome does not have to be so extreme. A sufficiently substantial atmosphere can transport heat from the day side toward the night side. Oceans could move energy as well. Clouds may develop in characteristic patterns. A tidally locked planet can therefore have complicated climates rather than simply dividing itself into one oven and one freezer. Whether any particular world remains habitable depends on atmospheric pressure, composition, ocean coverage, rotation, stellar radiation, and many other factors. The label habitable zone tells us mainly about the amount of energy received from the star. It does not certify the planet as comfortable. There is no cosmic estate agent inspecting the atmosphere and placing a green sticker in the window. Stellar activity creates a more serious challenge. Red dwarfs can produce powerful flares, especially when they are young and rapidly rotating. These events release ultraviolet and X-ray radiation. A planet orbiting close to the star receives a much larger dose than a distant planet would. Repeated high-energy radiation can alter atmospheric chemistry. In some circumstances, it may contribute to atmospheric loss, particularly if the planet lacks a strong magnetic field or has low gravity. The young life of a red dwarf can be especially difficult for nearby planets. Low-mass stars take a long time to settle onto the main sequence. During this extended early period, they can be considerably more luminous relative to their eventual stable output. A planet occupying the modern habitable zone may therefore have spent hundreds of millions of years receiving much more energy than it does today. Water on the surface could evaporate into the atmosphere. Ultraviolet radiation can split water molecules. Light hydrogen may then escape to space, potentially leaving the planet much drier. This possibility means that a world in a pleasant orbit today may carry the consequences of a far less pleasant youth. The problem is not necessarily fatal for every planet. A world may begin with a large supply of water. Volcanic activity can replenish atmospheric gases. A sufficiently massive planet may retain material more effectively. Atmospheric chemistry, magnetic fields, clouds, oceans, and the details of the star's activity all matter. The result is not a simple verdict, but a list of questions. That list is exactly why red dwarf planets are valuable. They allow astronomers to test how rocky planets behave under conditions very different from those experienced by Earth. Our solar system gives us one example of a life-bearing planet orbiting a G-type star. It does not tell us whether that arrangement is common, unusually favourable, or merely one successful route among many. If life can develop around red dwarfs, then the number of potential environments in the galaxy increases enormously because low-mass stars are extremely common. M-dwarfs are the dominant stellar population in the Milky Way. They are far more numerous than Sun-like stars, even though many are too faint to see with the unaided eye. Walk outside under a dark sky, and the stars that attract attention tend to be intrinsically luminous. The little red dwarfs remain mostly invisible. The night sky gives us a biased impression of what kinds of stars dominate the galaxy. It is rather like estimating the population of a city by counting only people carrying floodlights. The faint stars win through numbers. Their long lifetimes strengthen that importance. A sun-like star provides a relatively stable main sequence environment for billions of years. A low-mass red dwarf can remain active for hundreds of billions or even trillions of years depending on its mass. If a planet retains an atmosphere and remains in a suitable environment, the available timescale for biological or chemical evolution could be enormous. There is a complication here as well. A long stellar lifetime does not guarantee that a planet remains habitable for the same duration. Stellar luminosity changes, planetary interiors cool, atmospheres evolve, orbits can shift through interactions, geological activity may eventually decline. Still, the timescale forces us to reconsider the familiar idea that the life of the Sun is typical. The universe may spend far more of its future illuminated by small red stars than by stars like ours. Massive stars disappear quickly. Some live only a few million years. Sun-like stars survive for billions. Red dwarfs can continue for trillions. As cosmic star formation gradually declines, the bright short-lived stars will become less common. Long after the current generation of sun-like stars has evolved into remnants, many of the smallest hydrogen-burning stars could still be operating. The distant universe may therefore become increasingly dominated by objects that are unimpressive through a small telescope today. A star barely larger than a gas giant can outlast stars hundreds of times brighter. That relationship between brightness and lifespan is one of the useful lessons hidden in EBLM J0555-57Ab. Astronomy often draws attention toward extremes of size and power. The larger stars, hottest stars, fastest explosions, and most massive black holes naturally attract interest. The smallest stars show that another extreme matters just as much. They demonstrate how little mass is required for nature to build a stable nuclear reactor. They test how hydrogen behaves under enormous compression. They help locate the boundary between stars and brown dwarfs. Their eclipses provide measurements of stellar structure. They also improve our understanding of planets, because every planetary measurement depends on knowing the star correctly. Suppose a transit survey reports a planet twice the radius of Earth. If the host star's radius has been underestimated by 15%, the planet's radius has also been underestimated. The error then enters the calculated density. A world initially described as rocky might turn out to require a substantial volatile envelope. Another planet might move closer to the boundary between a large rocky super-Earth and a small gas-rich sub-Neptune. Temperature estimates depend on the star as well. A planet's equilibrium temperature is linked to the amount of radiation it receives. If the stellar luminosity is wrong, estimates of the planet's irradiation change. The location of the habitable zone moves with it. Atmospheric observations are also interpreted relative to the star's spectrum. Star spots, faculae, flares, and changes in activity can introduce signals that resemble or interfere with planetary atmospheric features. For red dwarfs, this is especially troublesome because many are magnetically active. When a planet transits across a spotted stellar surface, the measured spectrum may contain a mixture of information from the planet and from different regions of the star. A molecule apparently detected in a planetary atmosphere may require careful checking to ensure the signal did not originate from the star. Studying small stars in detail is therefore part of studying small planets. The two problems cannot be cleanly separated. This is one reason modern telescopes spend substantial effort characterizing host stars before making strong claims about their planets. Temperature, radius, mass, chemical composition, rotation, magnetic activity, and age all feed into the interpretation. The James Webb Space Telescope has pushed this work into the atmospheres of planets around tiny stars. TRAPPIST-1 remains one of the most closely watched examples. Its 7 Earth-sized worlds offer repeated opportunities to test what kinds of atmospheres can survive around an active ultracool dwarf. The results are already showing how difficult the problem is. Some of the inner planets do not appear to possess thick atmospheres of the kinds that could have been easily detected, while more temperate worlds remain under investigation. Finding an Earth-sized planet is one achievement. Determining whether it has air, water, climate, or conditions suitable for life is a much longer task. That distinction is important whenever we hear that a planet lies in the habitable zone. The phrase does not mean inhabited. It does not even mean habitable with certainty. It identifies a range of distances where liquid water could exist on a rocky surface if other conditions cooperate. Venus and Mars provide enough warning from our own solar system. Distance from the Sun matters, but atmospheres and planetary history matter just as much. Around a red dwarf, the uncertainties multiply, because we have no nearby example to inspect directly. A planet there may be tidally locked but climatically stable. It may have lost its atmosphere during the star's youth. It may have retained a thick atmosphere protected by gravity or replenished by geology. It may have oceans, ice, clouds, or almost nothing above bare rock. The only reliable approach is observation. That brings us back to why small stars are useful. Their planets provide stronger transit signals. Their low masses produce larger stellar wobbles. Their close inhabitable zones create short orbital periods. Nearby examples are bright enough in infrared wavelengths for increasingly detailed follow-up. They offer difficult environments and favourable measurements at the same time. EBLM J0555-57Ab helped establish just how small a hydrogen-burning star can become. Objects in that same broad low-mass regime now help astronomers investigate how small rocky planets form and survive. The connection is not that EBLM J0555-57Ab is secretly surrounded by an undiscovered second Earth. There is no need to give it planets that have not been observed. The connection is measurement. Before we can understand a planet crossing a tiny star, we need to know the dimensions of tiny stars. Before we interpret atmospheric spectra, we need to know their temperatures and activity. Before we decide whether a planet receives Earth-like radiation, we need a reliable stellar luminosity. A Saturn-sized star found while astronomers were searching for planets therefore feeds back into the search for planets. It helps calibrate the lower main sequence. It tests the models used to estimate stellar radii. Those models are applied to other low-mass stars. The improved stellar measurements produce improved planetary measurements. The effect spreads outward through astronomy from one very faint companion that was nearly mistaken for a large planet. There is another lesson in the mistake itself. Categories built from appearance can fail. EBLM J0555-57. AB looked planetary in radius. Its gravity revealed that it was stellar. Brown dwarfs can share the dimensions of giant planets while forming more like stars. White dwarfs can be roughly Earth-sized while containing a large fraction of a solar mass. Neutron stars can place more than a sun's worth of matter inside a region comparable to a city. The universe does not organize objects according to the diagrams most of us first encountered at school. Size is one measurement. Mass is another. Composition, internal physics, formation, temperature and age complete the description. Once that becomes familiar, the smallest known stars stop looking like exceptions and start looking like useful boundary markers. They show us where one set of physical rules begins giving way to another. Above the hydrogen burning threshold, gravity produces a core capable of maintaining fusion. Below it, degeneracy pressure prevents the same long-lived equilibrium. On either side, the radius hardly changes at first, making the boundary difficult to see. The transition is hidden inside. The same is true when astronomers study planets around red dwarfs. A small dark circle crossing a star tells us very little by itself. Mass determines whether it is rocky or gas-rich. Spectroscopy may reveal an atmosphere. Repeated observations may show weather or changing stellar activity. Every additional measurement removes another possible explanation. EBLM J0555-57Ab required that kind of patience. A shallow eclipse became a radial velocity signal. The velocity signal became a stellar mass. Correcting the extra light from a neighbouring star refined the radius. The final combination placed the object near the lowest edge of hydrogen-burning stars. That same habit of careful measurement now guides the search for worlds around other small stars. Some of those worlds may turn out to be airless. Some may have dense atmospheres. Some may spend one hemisphere facing their star. Some may have lost oceans before the star finished settling into its quiet main sequence life. A few may surprise us for reasons we have not predicted. The useful part is that these systems are increasingly within reach of observation. Their stars are faint, but their planets leave comparatively strong signals. Telescopes that cannot photograph a continent or ocean can still measure a planet's size, mass, orbit, temperature, and sometimes the chemistry of its atmosphere. Each measurement fills in a little more of the picture, and somewhere behind those planet searches remains the lesson of EBLM J0555-57Ab. Never assume that a small shadow belongs to a planet, never assume that a faint star is unimportant, and never assume that the objects producing the least light have the least to tell us. Having followed this small companion from its misleading transit signal, through its compressed interior, and out toward the planets that other red dwarfs may carry, there is one scale left to bring back into view. The star itself is only about the width of Saturn. The system is hundreds of light years away, and the light reaching us now began travelling long before anyone knew that stars could be this small. That distance gives us a useful place to return to the object as it actually appears from Earth. From Earth, none of this looks dramatic. There is no obvious tiny red star hanging beside Saturn for comparison. There is no visible label marking the point where ordinary stars finally become too small to continue. If you look toward the system with your own eyes, even under an exceptionally dark sky, EBLM J0555-57Ab would not reveal itself as the compact object we have spent all this time discussing. It is hundreds of light years away, buried in the glare of a brighter companion, contributing very little visible light of its own. The thing that made it famous was not how clearly we could see it, but how carefully astronomers could measure what it did. Every 7.8 days, the small companion crosses the face of the larger star from our point of view. A tiny fraction of the combined light disappears. The primary also moves back and forth because the little star pulls on it through gravity. Those two effects gave astronomers the clues they needed. The eclipse revealed something with the width of a giant planet. The stellar wobble revealed something much heavier. Put those measurements together, correct for the extra light from the third star in the system, and the strange result appears. Roughly 85 times the mass of Jupiter has been compressed into a body about the size of Saturn. That is still one of the easiest facts about EBLM J0555-57Ab to repeat, and one of the hardest to picture properly. We are familiar with Saturn as a planet. It has broad rings, a deep atmosphere, many moons, and a diameter that already seems enormous compared with Earth. If our planet were placed beside Saturn, Earth would look quite small. Now imagine removing Saturn and placing a genuine hydrogen-burning star in roughly the same amount of space. Not a dead star, not a white dwarf left behind after some larger object finished its life. not a neutron star compressed by a catastrophic collapse. A normal main sequence star. It simply happens to occupy the lowest end of what normal can mean. Deep inside, hydrogen nuclei are still combining through the proton-proton chain. Energy is being released, pressure is resisting gravity. The star remains in the stable condition that defines most of a star's life. Its output is modest compared with the Sun, but that is enough. A star does not have to produce daylight for a planet like Earth to qualify as a star. It does not need dramatic flares, a huge visible surface, or a starring role in anyone's night sky. It needs the right internal conditions. EBLM J0555-57Ab has them by a narrow margin. Reduce its mass enough, and the outcome changes. The core would still become hot during formation. Gravity would still squeeze the material. The object might even perform some limited fusion reactions while young. Eventually, however, electron degeneracy pressure would interfere with further heating before ordinary hydrogen fusion could establish a permanent balance. The object would become a brown dwarf. It would continue glowing from heat left over from formation, then slowly cool and fade. EBLM J0555-57. EB avoided that future because it formed with enough mass to cross the hydrogen burning threshold. Only a small difference in total material separates a body that spends its existence gradually cooling from one capable of burning hydrogen for an extraordinary length of time. That difference does not produce a large change in radius. This is why the bottom of the stellar main sequence is so strange. Add mass to an ordinary object and we expect it to become larger. Add mass to giant planets, brown dwarfs, and the very smallest stars, and increasing gravity compresses the material more strongly. A body can become much heavier without becoming much wider. Jupiter can therefore be larger in radius than a true star. That sentence would probably confuse a great many people if placed on a school poster without explanation. The categories we learn early in life encourage a neat progression. Moons are small, planets are larger, stars are enormous, galaxies are larger still. It is not a terrible introduction, but the universe becomes less cooperative once we start measuring individual objects. Some moons are larger than planets. Some white dwarfs are about the size of Earth despite containing an enormous amount of mass. Neutron stars pack stellar masses into regions only tens of kilometers across. Giant planets can be wider than the smallest stars. The diameter of an object tells us surprisingly little by itself. EBLM J0555-57. AB is a particularly useful reminder because its size initially helped it look like the wrong kind of object. The survey that noticed its eclipses was searching for planets. A body with a planetary radius passed across a much brighter star every few days. That was exactly the sort of signal the survey had been built to detect. Only the follow-up measurements showed how strong the companion's gravitational pull really was. The planet candidate became a low-mass star. A result that might have been treated simply as a failed exoplanet detection instead became one of the most interesting measurements near the stellar minimum. There is something useful in that sequence. Astronomy is full of discoveries that begin with an object refusing to fit the first explanation. A point of light is slightly too dim. A spectrum contains a line in the wrong place. A star moves more quickly than expected. An eclipse is the correct size for a planet, but the host star is wobbling far too strongly. The next step is not to force the observation back into the original category. It is to ask what else could produce the same signal. That is exactly what happened here. The small companion remained almost invisible beside the primary, but its gravity could not hide. Mass is difficult to disguise when another object is orbiting nearby. The result also gave astronomers a real test of theoretical models. Physics predicts that hydrogen-burning stars should stop existing below a narrow mass range. The precise boundary depends on composition and on the treatment of extremely dense hydrogen and helium. Finding objects near that boundary allows researchers to check whether the calculations match reality. EBLM J0555-57Ab lands very close to where the models say a star should barely be possible. Its radius is similarly valuable. Very low-mass stars are difficult to model perfectly. Their interiors are dominated by convection. Their atmospheres are cool enough for molecules to become important. Magnetic fields, rotation, star spots, chemical composition, and dense matter physics can all influence the predicted radius and temperature. A few percent may not sound like much, but a few percent in stellar radius becomes a serious problem when that same star is being used to measure a planet. A transit gives a planetary radius relative to the star. Get the star wrong, and the planet becomes wrong as well. This is one reason the smallest stars matter beyond stellar physics. They are among the most useful targets for finding small worlds. An Earth-sized planet crossing a Sun-sized star blocks only a tiny fraction of the light. Put the same planet in front of a much smaller red dwarf, and the transit becomes easier to detect. The planet has not grown. The background has shrunk. A low-mass star also responds more strongly to an orbiting planet's gravity, making radial velocity measurements more favourable. Its habitable zone sits closer to the star because the star produces less energy, so planets in that region complete their orbits more quickly. That gives astronomers more transits to observe. It also gives the planets a very different environment from Earth. Close-in worlds around red dwarfs may become tidally locked. Young red dwarfs can be magnetically active. Flares and high-energy radiation may affect planetary atmospheres. The long, bright pre-main sequence youth of a very low-mass star can expose nearby planets to much more energy than they receive later. A planet sitting comfortably in a red dwarf's modern habitable zone may therefore have had a rather uncomfortable childhood. Whether such worlds can retain oceans and atmospheres remains an active scientific question. There is no need for the answer to be simple. Some may lose almost everything. Others may begin with enough water or atmospheric material to survive. Geology could replenish gases. Clouds could alter temperatures. Oceans and atmospheres could transport heat around tidally locked planets. The point is not that small red stars guarantee good places for life. The point is that there are a great many of these stars. They live for extraordinary lengths of time, and their planets are becoming increasingly accessible to observation. EBLM J0555-57Ab itself is not the ideal example of a quiet red dwarf planetary system. It orbits a much brighter star at very close range, and the wider system contains a third stellar member. Its importance is more basic. It helps show us what the smallest true stars are physically capable of being. Barely wider than Saturn, dozens of times more massive than Jupiter, dense enough to produce surface gravity hundreds of times stronger than Earth's, faint enough to vanish beside a larger companion, massive enough to maintain hydrogen fusion. Those facts all belong to the same object. They also tell us something about how misleading brightness can be. When we look into the night sky, the stars we notice most easily are not necessarily the most common stars. Our eyes favour objects that produce enough visible light to stand out over long distances. Bright stars dominate the familiar constellations because bright stars are easy to see. Low-mass red dwarfs are much less impressive to human vision. Many nearby examples require telescopes, yet stars in that low-mass family are extremely common in the Milky Way. The bright night sky gives us a distorted census. If you walk through a city at night and counted only buildings with giant illuminated signs, you might conclude that almost every building was a theatre, casino, or restaurant, with unusually confident branding. The quiet buildings would disappear from your sample. Something similar happens when we judge the stellar population by eye. The faint stars are easy to overlook, but there are many of them, and they are remarkably persistent. The Sun will not remain a normal main sequence star forever. In several billion years, changes in its core will eventually drive it away from its present condition. It will expand, change structure, and pass through later stages of stellar evolution. The most massive stars have much shorter lives. They consume their fuel quickly and may disappear after only millions of years. The smallest red dwarfs take the opposite route. They release energy slowly. Their interiors can remain fully convective, allowing hydrogen from a large fraction of the star to be circulated into regions where fusion can occur. Their fuel is both consumed slowly and used efficiently. The result is a theoretical main sequence lifetime measured not merely in billions of years, but potentially in trillions. That number deserves a moment because our sense of cosmic time is usually built around the current age of the universe, roughly 14 billion years. A trillion years is more than 70 times that. 10 trillion years is more than 700 times the current age. The smallest stars have not existed long enough for astronomers to observe what their final natural evolution really looks like. We can model it. We cannot yet point to an ancient example and say, there it is. Every low-mass red dwarf currently visible is still young compared with the lifetime predicted for its class. The universe has not been around long enough for these stars to become old. That makes them unusual witnesses to cosmic history. A minimum mass star forming today could continue burning hydrogen long after the current arrangement of stars and galaxies has changed dramatically. It may outlive countless brighter objects that currently appear far more impressive. EBLM J0555-57. AB itself may not receive that entire isolated lifespan because it belongs to a close binary. Its primary companion will evolve much sooner and may eventually alter the small star's orbit or structure. Still, the physics demonstrated by its mass tells us what a tiny hydrogen-burning star can potentially do. The little object near the bottom of the main sequence is built for endurance. That is a rather different kind of stellar extreme. We often celebrate the biggest explosion, the hottest surface, the largest radius, or the fastest orbit. This object earns attention through restraint. It is almost as light as a star can be while remaining a star, almost as small as sustained hydrogen burning permits, almost faint enough to disappear completely beside its companion, yet almost is doing a great deal of work. The core crossed the threshold. Fusion started. The star remained a star. Somewhere around 600 light-years away, that process continues while we sit here discussing it. And the light carrying the evidence has spent centuries travelling toward Earth. Think about what that means in the most ordinary possible way. The photons arriving at a telescope tonight did not leave the system tonight. They did not leave last year. They did not begin their journey when the discovery paper was published. They were already moving through interstellar space while generations of people on Earth lived their entire lives without knowing this star existed. During that journey, telescopes were invented and improved. Newton developed his mechanics. Spectroscopy became a science. Photography changed astronomy. Einstein changed our understanding of space and time. Computers became capable of analysing tens of thousands of brightness measurements. Planet surveys began monitoring enormous areas of the sky. Only then did those old photons finally reach instruments capable of noticing that the brightness had changed by less than 1%. There was no announcement, just a small dip, then another one, then another, on schedule. That repeated pattern eventually led to spectra, velocity measurements, follow-up eclipses, corrections for nearby light, statistical models, and a conclusion that would have sounded rather odd before the data were assembled. A star can be about the size of Saturn. We should keep the wording careful. EBLM J0555-57Ab is commonly described as one of the smallest known hydrogen-burning stars, and at the time of its discovery, was presented as the smallest star with a well-measured radius. The universe is much too large for us to guarantee that no smaller star exists somewhere else. There may be another object with slightly less mass and a slightly smaller radius waiting inside a binary system we have not examined closely enough. A future survey may find it. Better instruments may revise old measurements. The record may change. That would not make EBLM J0555-57Ab less useful. Scientific records are interesting partly because they show how far observation has reached at a particular moment. The real value is the physical boundary the object helps us examine. Where does a star stop? How much mass is required? How does dense hydrogen behave near that limit? How small can a fusion-powered object become? How well do our models predict its radius? What happens to such a star over trillions of years? How accurately must we understand these stars before we can understand the planets around them? Those questions remain even if another object eventually takes the size record by a few kilometers. For tonight, however, EBLM J0555-57Ab gives us a very good place to leave them. At the beginning, I asked where you were listening from and what time it was in your part of the world. If you're still awake, the answer has changed slightly. A few more minutes have passed. Perhaps the room has become quieter. Maybe the traffic outside has thinned. Perhaps a screen is the brightest thing nearby, or there is only a little light coming through a curtain. Wherever you are, the small star has continued through part of another orbit while we've been here. It circles its primary every 7.8 days, so even the length of one long listening session represents a measurable fraction of that journey. Nothing about the system requires our attention. The primary continues shining. The small companion continues moving. Hydrogen continues fusing inside it. The distant third star continues on its much wider path. Their light continues outward in every direction, and a tiny portion eventually reaches Earth. Most of that light tells us almost nothing until we compare it carefully with the light that arrived before it. Then the pattern appears, a shallow eclipse, a shifting spectrum, a hidden mass, a surprisingly small radius. The star becomes measurable without becoming visible in the ordinary sense. If this quiet tour through one of the smallest known stars helped you settle down, you can leave a like, subscribe to Science for Sleep, and tell me where you're listening from tonight. You can also tell me what time it is there now. By the time you type the answer, it will already be a slightly different time, which feels appropriate after spending so long with an object whose light has travelled for centuries before reaching us. For now, there is nothing else you need to calculate. You do not need to remember the catalogue number. You do not need to keep 85 Jupiter masses, a Saturn-sized radius, a 7.8-day orbit, and the hydrogen burning limit arranged neatly in your head. The simple version is enough. Far away, a very small star circles a larger one. It is smaller than we once expected a normal star could comfortably be. Its first appearance resembled a planet. Its gravity gave it away. Inside, hydrogen continues to fuse slowly enough that an isolated star of similar mass could remain active for trillions of years. That small object gives astronomers a way to test the lowest edge of the stellar main sequence, and a better understanding of the tiny stars around which we are increasingly searching for other worlds. And here on Earth, all of that information reaches us as faint light, a little less light during an eclipse, a tiny shift in a spectral line, measurements small enough to miss unless someone knows where to look. That is often how astronomy works. The universe does not always reveal its most interesting objects by making them brighter. Sometimes it makes them just measurable enough. Sleep well, wherever you are listening from, and leave that little star to continue its orbit without us for a while.